Imagine waking up tomorrow, but it isn't tomorrow. It's asterisk yesterday. You stumble into your kitchen, and the coffee you spilled on the floor starts to creep back together, a dark puddle gathering itself from the tiles, defying gravity, and leaping back into your cup. In the pan, last night's scrambled eggs begin to uncook, the yellow curds smoothing themselves into a perfect, unbroken yolk, which then zips back into a pristine, uncracked shell. This strange, impossible reversal is prevented by a single, fundamental law of the universe. It's why the past is gone forever, why shattered glass never reassembles, and why you remember what you had for breakfast but have no idea what you'll have for dinner. But here's the puzzle. The deep-down laws of physics, the very equations that describe reality, don't seem to care about the direction of time. A planet orbiting a star looks perfectly normal whether you play the video forwards or backwards. So why is our experience of time a one-way street? What is this invisible current that drags us relentlessly from the past and into the future? And most importantly, what would happen if that current were to suddenly, inexplicably, reverse? Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The one-way street of time. We all feel it. Time, as we experience it, is an arrow. It gives our existence a one-way direction, an asymmetry. And that isn't just a poetic metaphor, it's one of the most obvious and profound features of our reality. Think about it. We get older, we don't get younger. We build up memories, they don't erase themselves as we head back toward birth. A building weathers and crumbles over centuries, it doesn't spontaneously assemble itself from a pile of dust. This is what physicists, starting with Sir Arthur Eddington back in 1927, dubbed the arrow of time. It points in one direction only, from past, to present, to future. You see this arrow everywhere. Drop an egg, and it splatters. You'll never see a puddle of yolk and shell leap back together to form a perfect egg. Mix cream into your coffee, and the two liquids will swirl into a uniform beige. No matter how long you stir, you'll never see the cream unmix itself, gathering back into a distinct white cloud. These events are what we call irreversible. The forward process feels natural, inevitable. The reverse? It feels like a film being rewound, a trick, an impossibility. The strangest part is that most of the fundamental laws that govern the universe, the rules of gravity, electromagnetism, and the strong nuclear force, are time-symmetric. The equations work just as well forwards as they do backwards. If you watched a video of two particles colliding, you wouldn't be able to tell if it was playing in forward or reverse. There is one known exception. The weak nuclear force, which was directly shown to violate this time symmetry in experiments like those at Babar in 2012. But for the most part, the universe's basic rulebook seems to be impartial to time's direction. This creates a massive contradiction, a deep puzzle physicists have wrestled with for over a century. If the fundamental rules don't have a preferred direction for time, why does our world, the world of eggs and coffee and people, so clearly and stubbornly move in only one direction? This one-way flow seems to be tied to three connected ideas. First, there's the psychological arrow, our perception. We remember the past, but we can't remember the future. Our consciousness seems to be built on an accumulation of past events, forming a continuous story that moves in one direction. Second, there's the cosmological arrow, which points in the direction of the universe's expansion. Since the Big Bang, the universe has been getting bigger, giving a clear, forward direction on a cosmic scale. But the most important one, the one that underpins all the others, is the thermodynamic arrow of time. This is what explains why eggs break and don't unbreak. It's governed by a concept so fundamental it dictates the fate of the entire universe, a concept called entropy. And it's this idea that holds the secret to why time, for us, only marches forward. Introducing the hero. Entropy. To understand the arrow of time, you first have to understand its master. Entropy. The word might sound complex, but the idea at its core is surprisingly simple. Entropy is just a measure of disorder, randomness, or messiness. The more disordered something is, the higher its entropy. Picture a brand new deck of cards. It's perfectly ordered. Ace, king, queen, jack, and so on, for all four suits. This is a state of very low entropy. It's highly ordered and very specific. Now, give that deck a good shuffle. The cards are now in a random, jumbled mess. This is a state of high entropy. It's disordered. And here's the key. There's only one way for the cards to be in that perfect, factory-ordered state. But there are a staggering number of ways for them to be jumbled up. The number is astronomically large, 52 factorial, a number with 68 digits. If you shuffle the deck, the odds of it landing back in that one, perfect, low-entropy state are practically zero. It's not impossible, just fantastically, mind-bogglingly improbable. The universe, at its core, is a game of probability. And it always bets on the most likely outcome. The most likely outcome is always more disorder. This is why a clean room, if you leave it alone, will naturally get messy. There are vastly more ways for clothes and books to be scattered around, high entropy, than for them to be neatly arranged on shelves, low entropy. Any system will always tend to move from a state of low probability to high probability, from order to disorder. This natural slide towards messiness is the essence of entropy. Physicist Ludwig Boltzmann was the first to nail this down in the 1870s. He realized that entropy is just about counting the number of ways you can arrange the microscopic parts of a system like atoms or molecules without changing how it looks on a large scale. For a melting ice cube, there are far more possible arrangements for the water molecules in a disorganized puddle, high entropy, than locked in a rigid, ordered crystal, low entropy. So, ice melts. It's not being pushed by some mysterious force. It's just giving in to the overwhelming odds. The increase of entropy is the one phenomenon that underlies every example of time's arrow. Our aging bodies, our accumulating memories, the very idea of cause and effect, it can all be traced back to this relentless, statistical march from order to chaos. The past is different from the future because the past had lower entropy. The universe was more ordered yesterday than it is today. And it will be even more disordered tomorrow. This isn't just a suggestion, it's one of the most fundamental and unbreakable laws of nature. The unbreakable law. The second law of thermodynamics. If entropy is the hero of our story, then the script it follows is the second law of thermodynamics. This law is one of the most powerful principles in all of science. It states, simply, that the total entropy of an isolated system can never decrease over time. An isolated system is one that doesn't interact with its surroundings, and for our purposes, the universe as a whole is the ultimate isolated system. The law says that for any natural process, the total disorder of the universe will either increase or, at best, stay the same. It will never, ever go down. This law explains why heat always flows from a hot object to a cold one. When you put a hot cup of coffee on a table, it cools down as the surrounding air warms up slightly. Energy disperses from a concentrated state, the hot coffee, to a more spread out state, increasing the overall entropy of the room. You will never see a lukewarm cup of coffee spontaneously suck heat out of the air to become hot again. That would cause the total entropy of the room to decrease, violating the second law. Let's go back to our broken egg. The whole egg is a highly ordered, low-entropy system. When it shatters, it transitions to a high-entropy state. The molecules are splattered in a chaotic mess. To unbreak the egg, every single scattered particle would have to spontaneously reverse its path, leap into the air, and reassemble itself into that one, specific, low-entropy arrangement. The statistical odds against this are so small it's practically impossible. It's not that the laws of physics forbid a single particle from moving in just the right way. It's that getting trillions upon trillions of particles to all do the right, coordinated thing at once is so improbable you would have to wait longer than the age of the universe to see it happen. The second law isn't a rule enforced by some cosmic police force, it's a statistical certainty. This is the very essence of the thermodynamic arrow of time. Time moves in the direction of increasing entropy. The future is the direction of more disorder. The past is the direction of less disorder. This isn't just an observation, it's practically a definition. The reason we experience time moving forward is because we are living in a universe that is constantly shifting from a state of lower entropy to a state of higher entropy. But this raises an even deeper question. If the universe is destined to get more and more disordered, it must have started in a very special condition. Why was the universe so tidy in the first place? To find the source of time's arrow, we have to go all the way back to the beginning. The ultimate origin story. The Big Bang's low entropy. The second law of thermodynamics explains why the universe gets messier over time. But it leaves a huge question unanswered. Why did the universe start in such a highly ordered state? If disordered states are so much more probable, shouldn't the universe have just started as a chaotic mess? The fact that it didn't is the ultimate mystery, and the answer is at the dawn of time itself. The Big Bang. About 13.8 billion years ago, the entire observable universe was squished into a space smaller than an atom. It was unbelievably hot and dense, but it was also in a state of incredibly low entropy. All the matter and energy were spread out with almost perfect uniformity. Now, this might sound backwards. A smooth, uniform gas seems more disordered than a universe full of complex galaxies and stars. But when gravity is the main force in play, the opposite is true. In a universe ruled by gravity, a smooth, uniform soup of matter is a highly ordered, low-entropy state. Think of it like a pencil balanced perfectly on its tip, a very specific, precarious setup. The slightest nudge will make it fall into a more stable, less ordered position on its side. In the same way, the uniform gas of the early universe was gravitationally unstable. Gravity wants to pull things together. Over billions of years, that smooth gas, under the relentless pull of gravity, began to clump. It formed stars, galaxies, and massive black holes. This clumpy state, surprisingly, is a much higher entropy state for the universe. A single black hole contains an enormous amount of entropy, far more than the uniform gas it formed from. So, the great puzzle of time's arrow isn't why entropy is increasing now, but why it was so shockingly low at the very beginning. This initial low entropy condition of the Big Bang is what scientists call the past hypothesis. It's the ultimate source of all the order we see. It's the reason stars shine, the reason life can exist, and the reason we have an arrow of time at all. The universe began in a highly improbable, exquisitely ordered state, and it has been unwinding into a more probable, disordered state ever since. Every irreversible process we see, from a star burning fuel to milk mixing in coffee, is just a small step on this grand cosmic journey from the pristine order of the Big Bang to the ultimate chaos of maximum entropy. The arrow of time isn't a property of time itself. It's a property of our universe's specific history. It's a feature that emerged from the universe's unique starting point. So, now we have our answer. Time flows forward because the universe started ordered and is moving towards disorder. And with that, we can finally ask the ultimate question. What if we could flip the switch? What if the universe suddenly decided to travel in the other direction, not towards more chaos, but back towards order? What would a world where time runs backward actually look like? What if we flipped the switch? The world in reverse. If the arrow of time were to reverse, the universe would start a journey toward decreasing entropy. The consequences would shatter reality as we know it. The most fundamental rule of our existence, cause and effect, would be flipped on its head. In our world, cause comes before effect. A cue ball hits the 8 ball, causing it to roll into the pocket. In a time-reversed world, you'd see the 8 ball roll out of the pocket and strike a stationary cue ball, which would then recoil. The effect would come first, and the cause would follow. Imagine seeing shattered glass on the floor. The shards would suddenly leap into the air, assembling into a perfect pane just in time for a baseball to fly backwards out of the window and land in a child's glove. Every event would be a prediction of its own cause. There would be no surprises, only fulfillments. Our very lives would become a film playing in reverse. We would emerge from the ground as decaying matter, reassembling into elderly bodies. Instead of celebrating birthdays, we'd mark the day we get a year younger. Wrinkles would smooth out, hair would regain its color, and we'd grow smaller and sprier with each passing year. We wouldn't learn, we'd unlearn. Each day, we'd forget things, our minds shedding knowledge and experience as we journeyed back toward infancy, finally culminating in our unbirth, returning to the womb. Memory itself would be an alien concept. Our psychological arrow of time is tied to the thermodynamic one. We create memories, ordered patterns in our brains by increasing the entropy of our surroundings, by eating food and generating heat. In a time-reversed world, would we remember the future? From our perspective, their future is our past. They would remember events that are, from their point of view, yet to happen. They'd know exactly what was coming tomorrow because for them, it had already happened. Their past, our future, would be a complete mystery. The wisest among them wouldn't be the one who had lived the longest, but the one who had forgotten the most. The world would be a constant spectacle of impossible reassembly. Smoke would pour down from the sky and flow back into chimneys. A car's exhaust would be sucked into its tailpipe, combining with oxygen to create fresh gasoline in the tank. Instead of eating, we would regurgitate fully formed food onto our plates, a process that would energize our bodies. We would breathe in carbon dioxide and exhale oxygen, while plants would do the opposite. The laws of physics themselves would seem to operate in reverse. Heat would flow from cold things to hot things. An ice cube dropped in water would grow larger and colder, while the water around it began to boil. If you dropped a ball, it wouldn't fall. Instead, it would leap from the ground into your hand, its potential energy increasing as it moved away from the earth. And yet, here is the most mind-bending part. For someone living in this reverse time universe, nothing would feel strange at all. Their reality would be completely self-consistent and logical to them. From their perspective, they would be moving forwards, from their past to their future. The second law of thermodynamics would still hold, but for them, it would state that entropy is always decreasing, and that would be their arrow of time. Their cause and effect would be our effect and cause. It would be a perfectly valid, functioning universe, just one that is the mirror image of our own. Is a reversal even possible? The quantum realm and beyond. Having painted a picture of this bizarre, reversed reality, we have to ask, could it actually happen? On the large scale of people, planets, and galaxies, the answer is a resounding no. The second law of thermodynamics is a statistical monster. The odds of a spontaneous, large-scale decrease in entropy are so small they are practically zero. Your spilled coffee will never leap back into its cup. The universe will not start running backward. However, when we zoom down to the fuzzy world of quantum mechanics, the picture gets a little less certain. Some theories and recent studies suggest that at the microscopic level, the arrow of time might not be so absolute. Physicists have explored open quantum systems, tiny systems that interact with their environment, and found that it might be possible for opposing arrows of time to emerge. Some 2025 research suggests that even when you factor in things that should enforce a direction, time symmetry can remain, hinting that time could theoretically move both ways at this fundamental level. These aren't events we could ever see, but they hint that reality's fabric might have tiny, fleeting reversals in time's flow happening all around us. Other experiments have demonstrated a phenomenon called temporal reflection. By sending an electromagnetic wave through a special material and suddenly changing its properties, scientists were able to make part of the wave effectively reverse its path in time, creating a backward copy of itself. This isn't time travel like in science fiction, but it shows that under very specific, engineered conditions, the flow of a process can be temporally reversed. On a cosmic scale, the question of reversal is tied to the universe's ultimate fate. The current consensus model suggests the universe will expand forever towards a state of maximum entropy known as heat death, or the Big Freeze. In this scenario, the arrow of time marches relentlessly in one direction. However, an older theory, the Big Crunch, hypothesized that gravity might one day stop the expansion and cause the universe to collapse back in on itself. Some physicists, including Stephen Hawking, once speculated that during this collapse, the arrow of time itself might reverse. While Hawking later concluded he was wrong and the Big Crunch is no longer the favored model, it remains a fascinating idea. Some modern theories even propose that our Big Bang might have created two universes. Our universe, expanding forward in time, and a mirror universe, expanding backward in time from our perspective. For anyone in that universe, we would be the ones moving backward. This is highly speculative, but it opens the door to the mind-boggling possibility that a time-reversed reality isn't just a hypothetical, but could be a parallel existence, forever beyond our reach. The unseen architect. Why we are creatures of entropy. So, what have we learned? The arrow of time, that current that pulls us from past to future, isn't a fundamental property of time itself. It's an emergent feature, a consequence of two simple facts. The universe began in an incredibly ordered, low-entropy state, and the laws of probability say it must move towards more disorder. The past is gone forever, not because of some mysterious law of time, but because of an unbreakable law of statistics. Our very existence is built on this forward flow of entropy. Life itself is a magnificent, ongoing battle against the second law. A living organism is a highly ordered, low-entropy system. To maintain this order, to build cells, think thoughts, and move muscles, we must constantly increase the entropy of our surroundings. We take in low-entropy energy, like food, and degrade it into high-entropy energy, heat, to power our bodies and fight off the natural tendency to decay. Life carves out little pockets of order in a universe that is sliding towards chaos. Even our consciousness is a product of entropy. The psychological arrow of time, our ability to remember the past and not the future, is a direct result of the thermodynamic arrow. The past is the direction of lower entropy, a time when records and memories could be formed in an ordered state. The future is the direction of higher entropy, a realm of infinite disordered possibilities that can't be remembered, because it hasn't settled into a single state yet. We are creatures of entropy, surfing the wave of increasing disorder from the Big Bang into the unknown future. The feeling of time's passage is the feeling of the universe unfolding according to the laws of probability. In the end, the question, what if time started running backwards, leads us to one of the most profound insights in physics. The forward march of time isn't an illusion, but it's also not fundamental. It's a story. It's the story of a universe that was born in a state of exquisite perfection and has been getting progressively messier ever since. The shattered glass on the floor, the cooling cup of coffee, the wrinkles on our faces, they're all pages in this cosmic story of order becoming chaos. To reverse time would be to untell that story, to force the universe back into a state of impossible order against the overwhelming tide of probability. And while the laws of physics might permit it on a fleeting, quantum scale, our reality is bound to the statistical certainty of the second law. So, the next time you watch cream mix into your coffee or think about a memory from long ago, take a moment to appreciate the silent, powerful force at play. You are witnessing the arrow of time. You are seeing the echo of the Big Bang and the legacy of a universe that started with low entropy. You are experiencing the fundamental reason why tomorrow is always a new day and why yesterday is gone forever. In our universe, time isn't just a clock ticking. It's an arrow, carved by the relentless, beautiful, and inescapable growth of chaos. What other mind-bending physics concepts would you like us to explore? Do you think a mirror universe running backward in time could exist? Let us know in the comments below. And if you enjoyed this journey to the edge of reality, make sure to subscribe and hit the notification bell for more explorations of the biggest questions in the cosmos. The one law that traps us in the future. You can't unbreak a cup. You can't unmelt an ice cube. And you definitely can't unlive yesterday. We all know this. We feel it in our bones, right? It's the silent, invisible current pulling us away from the past and into an unknown future. The past is a landscape we can remember but never return to, while the future feels like an open sea of possibility. But have you ever stopped to ask why? Why does the movie of our lives only play forward? Why can't the universe just hit rewind? This isn't some rule we made up. It's not a philosophical suggestion or a quirk of our psychology. It's a law of the cosmos, written into the fabric of reality itself. It's as fundamental as gravity, but in many ways, it's far more powerful. And it's the one law that traps us and the entire universe in a one-way trip toward the future. Today, we're going on a journey to find this law. We'll start in your kitchen with a cup of coffee and end at the edge of time itself. By the end, you'll understand the profound physical reason why escaping the past isn't just difficult, it's statistically and cosmically impossible. Just imagine it for a second. A shattered coffee mug on the kitchen floor. Sharp, ceramic shards scattered in a total mess. Now, picture the world hitting rewind. The pieces slide across the floor, they rise, and they click back together with impossible precision as the mug leaps, perfectly whole, onto the edge of the table. Weird, right? It feels fundamentally wrong, like a glitch in the Matrix. It's the kind of thing that tells you you're dreaming. That deep, intuitive feeling, that certainty that things just don't happen this way, is your mind recognizing the most unbreakable rule in the cosmos. We're about to decode that feeling and turn it into a deep understanding of time itself. The everyday mystery. Before we get to the cosmic scale, let's stay in that kitchen. The world is filled with these one-way processes. They're so common we barely notice them. But if you look closely, each one is a clue in a grand detective story about the nature of time. Start with your coffee. You pour it, hot and steaming. That amazing smell fills the air. You set it on the counter and forget about it. When you come back 10 minutes later, what do you find? A lukewarm, sad cup of coffee. The heat has bled out into the room. Now, think about the reverse. Have you ever seen a cup of lukewarm coffee spontaneously start to warm up? Have you ever seen all the random air molecules in your kitchen conspire to gather their spare heat and focus it perfectly into your mug? Of course not. It sounds ridiculous. Heat flows from hot to cold. That's clue number one. And it's not just about heat. Think about our poor coffee mug again. It sits on the edge of the table, a single, ordered object. A tiny nudge, gravity takes over, and it falls. In that split second of impact, its singular, ordered form is destroyed. It shatters into 100 fragments. That energy from the fall becomes sound, that sharp crack, and a little bit of heat where the pieces hit the floor. The pieces lie scattered, a monument to chaos. Tipping the mug over was effortless. But reversing it? Could you gather the sound waves from the crack and turn them back into motion? Could the floor give back the heat from the impact to help fuse the ceramic? The idea is laughable. Order becomes chaos easily. Chaos almost never spontaneously becomes order. That's clue number 2. Our third clue is maybe the most relatable. The messy room. You can spend an afternoon cleaning your room. Books aligned, papers in neat stacks, clothes folded. This is a state of high order that took energy to create. Now, what happens over the next week? You don't have to try to make it messy. You just live. A book gets taken down and not put back. Mail gets tossed on the desk. A shirt is draped over a chair. Dust, which is just tiny particles of chaos, settles everywhere. Slowly but surely, the room drifts from its single, ordered state into one of a million possible messy states. A clean room is clean in one specific way. A messy room can be messy in an almost infinite number of ways. It seems the universe just has a natural tendency to explore all those messy options. So there we have it. 3 clues from daily life. A coffee that only cools. A mug that only breaks. A room that only gets messy. All of them point in the same direction. They're all following a one-way flow from order to disorder, structure to chaos. This isn't just a tendency. It's a law. The most powerful and far-reaching law in physics. It's called the second law of thermodynamics. And the thing it governs, this measure of chaos and disorder, is known as entropy. To understand entropy is to understand why time has a direction. Introducing the secret law, entropy. So, the universe has a clear bias for messiness. This preference is written down in the second law of thermodynamics, which basically states that in any closed-off system, the total amount of entropy, or disorder, will always increase or stay the same. It never, ever goes down on its own. This law is a big deal. The British scientist Arthur Eddington once said it holds the supreme position among the laws of nature. He argued that if your new theory goes against the second law, it's doomed to collapse in deepest humiliation. But what is entropy? The word sounds intimidating, but the concept is surprisingly simple. We often say disorder, but a better way to think about it is probability. Entropy is just a measure of how many different ways a system can be arranged. High entropy means there are tons of possible arrangements. Low entropy means there are very few. Let's make this real. Imagine a brand new deck of playing cards, arranged by suit and then by rank, ace to king. This is a state of very low entropy. Why? Because there is only one way for a deck to be in this perfect order. Just one specific arrangement. Now, you shuffle the deck. You toss the cards in the air, you mix them up. You've introduced randomness. The cards are now in a jumbled, chaotic, high-entropy state. But here's the key question. Why is it a high-entropy state? Not because messy is a magical force. It's because there are an astronomical number of ways for a deck to be shuffled. The number of possible ways to arrange a 52-card deck is 52 factorial. That's a number so big it's hard to wrap your head around. It's an 8 followed by 67 zeros. If every star in our galaxy had a trillion planets, and every person on each planet had been shuffling cards every second since the Big Bang, they wouldn't have even made a dent in all the possible combinations. So, think about it. There's one arrangement that's perfect order, and there are roughly 80 unvigintillion arrangements that count as shuffled. If you shuffle a deck, what's the probability you'll land on that one perfect, low-entropy state? For all practical purposes, it's 0. It's not that it's physically impossible, it's just so comically improbable that it will never, ever happen. The deck naturally moves toward the states that are overwhelmingly more probable, the shuffled, high-entropy ones. This is the secret of the second law. It's not a law of force, like gravity. It's a law of statistics. Things get disordered because there are just unimaginably more ways to be disordered than to be ordered. Think of gas in a box with a divider. On the left, we have a cloud of purple gas. On the right, a vacuum. This is an ordered, low-entropy state. Now, we remove the divider. What happens? The gas molecules, all bouncing around randomly, immediately spread out until they're evenly distributed. The system has moved to a high-entropy state. Again, why? No force pushed them. It was pure probability. The odds of the trillions upon trillions of molecules all randomly deciding to hang out in the left half of the box are so infinitesimally small, we can just call it zero. The universe is constantly shuffling its atoms and energy. And just like the deck of cards, it's always moving toward the most probable outcome. And the most probable outcome is always the one with the highest entropy. A state where heat is spread out is more probable than one where it's all in your coffee cup. A state where a mug is in pieces is more probable than one where it's perfectly whole. The universe isn't choosing chaos. It's just playing the odds. And that simple fact is the key to unlocking the mystery of time. The arrow of time. Okay, so we have this fundamental rule. Entropy always increases. This brings us to the heart of our question. How does a law about messy rooms and cooling coffee explain the flow of time? The connection was brilliantly described by Sir Arthur Eddington in his 1928 book, The Nature of the Physical World. He realized that this one-way nature of entropy was unique. Most other fundamental laws of physics like gravity or classical mechanics are time-symmetric. That means the equations work perfectly fine forwards or backwards. A video of a planet orbiting a star looks just as plausible in reverse. The laws of motion don't care about past or future. A few weird exceptions exist in the quantum world, but on the whole, physics doesn't have a preferred direction for time. But the second law changes everything. It's the great tiebreaker. It points in one, unambiguous direction. Eddington called it the arrow of time. He said that if you see the random element in the world increasing, you're looking toward the future. If you see it decreasing, you're looking toward the past. That's the only distinction physics knows. This thermodynamic arrow of time is what separates yesterday from tomorrow. The past is the state of lower entropy. The future is the state of higher entropy. It even explains why you remember the past but not the future. The act of forming a memory in your brain requires energy. It creates waste heat. It's a physical process that increases the total entropy of the universe. To remember the future would mean knowing the outcome of a probabilistic system before the dice have even landed, a violation of causality itself. Our psychological arrow of time is locked to the thermodynamic one. Think back to our examples. The coffee cools because that process increases the total entropy of the kitchen. Time flows in the direction of cooling. The mug shatters because the scattered pieces are a much higher entropy, more probable state. Time flows in the direction of breaking. But wait, what about when we clean our messy room? Aren't we decreasing entropy? Aren't we pushing time's arrow backward? This is a crucial point. You can absolutely create pockets of order. Life itself is a stunning example. And this is the most important. But in physics, you can only create that local order by creating an even greater amount of disorder somewhere else. When you clean your room, your body is burning calories and generating waste heat. The total increase in the universe's entropy from your efforts is far greater than the small decrease in entropy you achieved by stacking your books. A refrigerator makes its inside colder, lower entropy, but the coils on the back pump even more heat out into your kitchen. The universe's entropy ledger always comes out positive. You can build a sandcastle, but the sun's energy that powers your body and the waves that wash it away are all part of a larger system marching towards greater entropy. The second law is the universe's ultimate accountant, and the books must always balance in favor of chaos. This is why the past is gone forever. To go back would mean spontaneously decreasing the total entropy of the universe. It would mean the shuffled deck sorting itself or the shattered mug reassembling. And probability tells us this is so unlikely that it won't happen in the entire lifetime of the cosmos. The past is the ordered egg, the future is the scrambled mess. And you just can't unscramble an egg. Scaling up to the cosmos. We've seen how this law governs our kitchens. But its true power only becomes clear when we scale it up. Way up. If the universe is always getting messier, it leads to a huge question. Things must have started in a state that was incredibly, inexplicably ordered. And that's exactly what our best models of the universe tell us. The Big Bang, approximately 13.8 billion years ago, seems to have been the ultimate low-entropy state. This sounds confusing. We picture the Big Bang as a hot, chaotic soup. But on a cosmic scale, where gravity is king, ordered doesn't mean cool and neat. It means smooth and uniform. An even spread of matter and energy is an extremely low-entropy state because gravity wants to pull it all into clumps. The natural, high-entropy state for a universe with gravity isn't a smooth gas. It's a lumpy mess of stars, galaxies, and eventually, black holes. So, for reasons we still don't fully understand, our universe began in this highly improbable, low-entropy condition. It was like the entire cosmos was a brand new deck of cards, perfectly sorted and ready to be shuffled. And for the last 13.8 billion years, that's exactly what the universe has been doing. It's been following the second law, moving relentlessly towards higher entropy. The arrow of time that began at that first moment has been flying ever since. Every star is an engine of entropy. It forges simple hydrogen into more complex elements, a tiny pocket of order, but in doing so, it unleashes a torrent of disordered light and heat into the void, paying its entropy debt 1 trillion times over. Every star, every galaxy, every beautiful nebula is just a temporary stop on the one-way river flowing towards an inevitable end. And this brings us to the final, mind-bending destination. The ultimate fate of the universe. If entropy must always increase, where does it all end? The leading theory is known, chillingly, as the heat death of the universe. It's the logical conclusion of the second law playing out over unimaginable timescales. In this scenario, the universe continues expanding. Stars burn out. The universe goes dark. Over trillions upon trillions of years, even the dead stars and black holes are predicted to decay, slowly evaporating away into a faint mist of particles. While these timescales are still theoretical, the end result would be a vast, cold, dark, and empty universe. A near-perfect vacuum with a thin, uniform soup of particles at a temperature just above absolute zero. This is the state of maximum entropy. No structure, no complexity, no change is possible. And if there's no possibility of change, the arrow of time itself loses its meaning. The universe's long story will finally be over. So, let's go back to that broken cup on the floor. It's not just an accident. It's a small-scale demonstration of the most fundamental law of the cosmos. You can't unbreak a cup for the same reason you can't unlive yesterday. Because the universe is governed by probability. Because there are infinitely more ways to be broken than whole, more ways to be messy than neat, and more ways to be scattered than gathered. The one-way street of time isn't an illusion. It was born from the bizarrely ordered state of our universe's birth and is driven by the relentless ticking of the statistical clock. Every moment of your life, every thought you have, follows this forward flow from the low entropy past to the high entropy future. The law that shatters a glass is the same one that set galaxies in motion and dictates the ultimate fate of everything. We are living in the universe's long, slow, beautiful exhale, a glorious, temporary journey from pristine order toward a final, uniform chaos. We are trapped on a one-way trip into the future, because the future is, quite simply, the path of least resistance. If this journey into the laws of time blew your mind, make sure to subscribe and hit that bell so you don't miss our next exploration. And let me know in the comments, what other cosmic mysteries keep you up at night? I lived in a universe where entropy reversed. It started with a broken egg. I just stood there, watching as the yolk and white flowed backward, pouring themselves into the reassembling shell. The crack sealed itself shut, and the egg lifted right off the floor, landing perfectly whole in my hand. This wasn't magic, and I wasn't dreaming. I was in a universe where the arrow of time had shattered, and everything broken was impossibly becoming whole again. This is my story of a world where chaos turned into order, where the most fundamental rule of our cosmos wasn't just bent, but completely reversed. The first signs. The unraveling of the everyday. That first day was a series of quiet, impossible moments that just didn't make any sense. The egg was only the beginning. I remember putting my hand on a mug of coffee I'd left on the counter for hours. It was cold, of course. But then, a strange warmth bloomed against my palm. It wasn't my heat, it was coming from the mug. Steam began to rise from the coffee, not in a gentle wisp, but like it was being sucked back into existence. The air around the mug got colder as the coffee got hotter and hotter, until it was scaldingly fresh again, as if all the lost heat in the room had decided to gather right back in that one cup. I walked through my house like it was a museum of tiny miracles. A faint, lingering smell of burnt toast in the kitchen pulled back from the corners, gathering right above the toaster until the scent was just gone. A wilting flower on the windowsill started to stand up straight, its brown petals regaining their vibrant red color. Outside, the world was performing the same, subtle, unsettling dance. A puddle from the morning's rain was shrinking, not by evaporating, but by retreating into itself. It was as if the water vapor in the air was condensing and flowing back into the puddle, making it whole again. A spider's web, torn by the wind, was meticulously rethreading itself, each strand finding its lost connection. It all just felt so profoundly wrong. Our lives are built on cause and effect. Things break. They cool down. They decay. That's the way it's supposed to be. But here, the order was flipped. I could see the end of something, and then watch it unhappen. It wasn't violent. It was unnervingly quiet and precise. The universe was cleaning itself up. That night, I lit a candle, just to see something normal. I watched the flame for an hour as the wax melted and dripped down the side. Then, I blew it out. A plume of white smoke rose into the air, but then it just stopped. The smoke hung there for a second, then it all started flowing backward, pouring right back into the wick. The blackened wick turned pale again, and the melted wax crawled back up the side, until the candle was pristine, even taller than when I'd lit it. It was like it had never been burned at all. In that moment, watching the smoke pour back into the candle, I knew this wasn't just some local fluke. To understand how my world had been turned inside out, I had to understand the engine that drives our universe forward. Entropy. The physics of impossible things. What is entropy? To really get how impossible all this was, you have to know what entropy actually is. We hear the word a lot, usually tossed around to mean disorder or randomness. But that's like calling the ocean wet. It's true, but it misses the point. The second law of thermodynamics, one of the most solid rules in all of physics, says that the total entropy, or disorder, of an isolated system can only ever increase over time. It never, ever goes down. That's why your coffee gets cold, and that's why your room gets messy. It's the arrow of time. Think about a new deck of cards, perfectly ordered from ace to king. That's a low entropy state. There's only one way for it to be perfectly ordered. Now, shuffle it. The cards are now in a disordered, high entropy state. Why? Because there are trillions upon trillions of ways for the cards to be messy, but only one way for them to be perfect. The universe doesn't prefer messiness, it's just playing the odds. A system naturally drifts toward a state of higher entropy simply because there are overwhelmingly more ways to be in that state. It's pure probability. Think of a drop of ink in a glass of water. At first, the ink is altogether low entropy. As the molecules bounce around, they spread out. Now, is it possible for all those ink molecules to randomly bounce their way back into a single drop? Yes, technically. But it's so statistically unlikely that you would have to wait longer than the age of the universe to see it happen. The odds are basically zero. This is what drives every irreversible process we know. Heat flows from hot to cold because energy is more disordered when it's spread out. An egg breaks because there are countless ways for it to be a splattered mess, but only one way for it to be a whole egg. This isn't a suggestion. It's the one law of physics that tells the past from the future. You can watch a video of a planet orbiting a star forward or backward and not know the difference. But if you watch a video of an egg shattering, you know instantly if it's in reverse. The increase of entropy is what gives time its direction. So in my universe, this fundamental law of probability had been turned on its head. The universe was now overwhelmingly more likely to fall into states of lower entropy. The shattered egg wasn't being magically glued back together. In this new reality, the state of being a whole egg was simply the most probable outcome. The universe wasn't falling into chaos anymore. It was climbing, with statistical certainty, toward a state of perfect, terrifying order. A world in reverse. The consequences escalate. The weirdness of reassembling objects quickly gave way to a much deeper sense of unreality. The world didn't just clean itself, it began to uncreate itself. I noticed it in nature first. A walk in the woods felt like a journey backward in time. Fallen leaves would lift from the ground and reattach themselves to branches. Old, gnarled trees seemed to be smoothing out, their bark becoming less furrowed. Erosion, the great sculptor of our world, started working in reverse. Pebbles at the bottom of a stream would slowly roll against the current, making their way back up the mountains they'd worn away from. Rivers that once carried silt to the sea now flowed with impossible clarity, pulling sediment from their deltas and carrying it back upstream, rebuilding the land. But the most horrifying changes were happening to life itself. An organism is a highly ordered system that stays that way by consuming energy and increasing the disorder of its surroundings. We eat, we break down food, and we release heat, increasing the total entropy of the universe just to maintain our own little pocket of order. In my new reality, this whole process was flipped. Digestion became an act of creation. My body started taking in simple molecules and waste products and reassembling them into complex food. The feeling of hunger was replaced by a strange, unpleasant fullness that only went away after I unate. A process I really don't want to describe, but that ended with fully formed food leaving my body. I no longer gave off heat. My body became a heat sink, pulling in warmth from my surroundings. I had to wear layers of clothes not to stay warm, but to stop my body from constantly absorbing heat from the room. Breathing was inverted. My lungs expelled oxygen and drew in carbon dioxide, which my cells used to rebuild complex molecules. Life was running in reverse. And then, there was memory. This was the most disorienting part. Our sense of time that we move from a known past to an unknown future is tied to the arrow of time. We remember the past, not the future. But what happens when the direction of order is the future? My memory started to work backward. I wouldn't remember things that had just happened. I'd remember things that were about to unhappen. I knew the end of a conversation before it began. I'd walk into a room to get something, and only as I was leaving with it would the memory of needing it arrive. Causality was broken. The future wasn't a world of possibilities anymore. It was a fixed, ordered state that I was moving away from. The past, meanwhile, became a chaotic, unknowable fog. My own identity started to fracture. I was a being built of memories of a future I was destined to undo, living backward, like a ghost moving away from his own grave. Okay, I have to pause here. This stuff is mind-bending, right? If you love digging into these huge, what if, questions about our reality, do me a favor and hit that subscribe button. We go down rabbit holes like this all the time. Alright, now back to the world falling apart. Or, rather, falling together. The cosmic rewind. The effects I was seeing on Earth were just local symptoms of a universal transformation. On a cosmic scale, the reversal of entropy was staging a drama of unimaginable proportions, undoing the very history of the universe. For billions of years, our universe has been expanding and cooling as its entropy increases. Stars burn through their fuel, radiating heat and light into the void. In my new universe, this grand process was running backward. Looking at the night sky, the stars seemed to burn with a strange, cold fire. They weren't radiating energy, they were absorbing it. Faint clouds of gas and dust, the remnants of dead stars, were slowly pulling themselves back together. Stars weren't dying in brilliant supernovae, they were being born from them. A supernova, the ultimate act of cosmic disorder, was now an implosion, a chaotic cloud of debris rapidly coalescing into a single, perfect point of light. Galaxies were unspinning, their graceful arms tightening. The expansion of the universe had stopped and reversed. Every galaxy was now moving toward every other galaxy. The redshift of distant galaxies, our key evidence for an expanding universe, was replaced by a universal blue shift. Everything was rushing toward a single point. The most profound reversal was happening to the cosmic microwave background, the afterglow of the Big Bang. This faint hiss of radiation, the most disordered feature of our universe, was becoming less uniform, its photons coalescing into hotter and hotter spots as they traveled backward in time. The universe was heading back to where it all began. A state of incredibly low entropy. I was living in a universe that was contracting towards a big crunch. But from my perspective, this wasn't an end. It was a beginning. The universe was contracting toward an infinitely hot, dense, and perfectly ordered state. It wasn't a grave. It was an egg that had already cracked and was now impossibly putting itself back together. I was witnessing the unhappening of creation. The snapback. The return to reality. My existence in this backward world was like a pencil balanced perfectly on its tip. It was so statistically unlikely that it couldn't possibly last. And it didn't. I don't know what triggered it, a random quantum fluctuation, maybe, but one moment, the world was rewinding, and the next, the switch flipped. They call it the snapback. It was instantaneous. It was catastrophic. The whole egg in my hand didn't just fall and break, it exploded. The hot coffee flashed into steam, scalding my hand as all its concentrated energy dispersed in a fraction of a second. The candle vanished in a burst of fire and smoke. The whole house was thrown into chaos, as if a whirlwind had just passed through. Outside, the world descended into madness. The river that had been flowing uphill instantly reversed, unleashing a tidal wave down the valley. The mountains let go in a series of catastrophic landslides. The very air erupted into a gale as molecules went back to their normal, random motion. For life, the snapback was an apocalypse. Biological processes that had been running in reverse were thrown into forward gear with explosive force. My body, which had been absorbing heat, suddenly released it in a wave of energy. Every cell, every nerve, every pathway that had been operating backward was violently wrenched back into its natural direction. The pain was absolute, a biological civil war fought inside my own flesh. The universe, in a single, terrifying instant, remembered its own nature. It remembered that it's easier to break than to build. The pencil balanced on its point had fallen. The comfortable, familiar, and destructive march of chaos had resumed its reign. The arrow of time was flying forward again, with a vengeance. Why the arrow only flies forward? This whole journey, this impossible thought experiment, is the ultimate illustration of why our universe works the way it does. It answers the big question: why does time only move in one direction? The answer is both simple and profound. Because the universe always moves toward the most probable state. And the most probable state is always one of higher entropy. The second law of thermodynamics isn't like other laws of physics. It's a law of pure statistics on a cosmic scale. A glass shatters into 1,000 pieces. Is there a force preventing those pieces from leaping back together? No. It's just that the number of ways those pieces can be scattered on the floor is astronomically larger than the one specific way they can form a glass. The universe isn't choosing disorder. It's just that the options for disorder are nearly infinite, while the options for order are painfully few. This statistical certainty is the engine of time. Our universe started in a state of incredibly low entropy, the hot, dense singularity of the Big Bang. For nearly 14 billion years, it's been unfolding into states of higher and higher probability. That forward march is what we perceive as the flow of time. Every experience you have is built on this. We remember the past, not the future, because the process of storing information in our brains increases entropy. You crack an egg, low entropy, and then you scramble it, high entropy. You never see it the other way around because you are a creature living inside this forward flow of universal disorder. Your very consciousness might just be your brain processing reality in sync with this fundamental cosmic current. The world I lived in, the world of decreasing entropy, was a statistical impossibility, a universe fighting its own nature. The snapback wasn't a punishment, it was an inevitability. It was the universe correcting a rounding error, collapsing from an impossible state back into the predictable reality of ever-increasing chaos. The arrow of time doesn't fly forward because it has to. It flies forward because that is the path of least resistance. Living in a world where entropy reversed was like watching a film of the universe playing backward. But this thought experiment reveals a deep truth about our own reality. The universe's relentless, one-way journey towards disorder isn't a flaw. It's what makes our existence possible. The increase of entropy drives all change. It allows for the messy, complex processes of life, evolution, and consciousness. It's the reason we have a past to remember and a future to build. The constant, irreversible shattering of order is what gives time its direction and our lives their meaning. The fact that eggs break and don't unbreak, that we get older and not younger, isn't a tragedy. It's the signature of a universe that is alive with possibility. So the next time you stir milk into your coffee and watch it swirl into a uniform, messy brown, take a moment. You're not just watching a simple act. You're watching the arrow of time in action. You're watching the very engine of the cosmos, the law of probability that ensures the film of our lives only ever plays forward. So, what do you think would be the strangest part of living in a universe where entropy reversed? Let me know your thoughts in the comments below. And if you want to continue exploring the biggest questions in the cosmos, make sure to subscribe and turn on notifications so you don't miss our next journey into the wonders of science. You start aging backwards tomorrow. What happens next? You wake up the day after your 30th birthday, and something just feels off. It's not a hangover, and it's not the creeping dread of a new decade. It's something lighter. You glance in the mirror, and that tiny laugh line by your eye, the one you've been tracking with mild alarm for 6 months, seems like it's faded. You shrug it off. Must be a trick of the morning light. A good night's sleep, for once. But the next day, you know it's not a trick. You feel a new energy, a kind of vitality you haven't felt since your mid-20s. The day after that, a colleague squints at you over their monitor. "Have you been on vacation?" they ask. You look rested. By the end of the week, you know it's not in your head. You pull out your driver's license, a photo taken on your 28th birthday, and hold it up to your reflection. The face staring back from the mirror is undeniably younger. It feels like a miracle. A private fountain of youth delivered right to your doorstep. Then you turn on the news. It's not just you. It's everyone. Everyone on the planet who just turned 30. A strange, inexplicable, global phenomenon has begun. The day you turn 30 is your peak. And after that, the countdown starts. Your life is no longer a journey toward old age, but a slow, steady march back to the moment you were born. This is the story of how the world learned to live in reverse. At first, the world explodes in a kind of manic joy. The media dubs it the reversal, and it's hailed as the end of aging, the death of decay itself. It feels impossible, a beautiful violation of natural law. Physicists, scrambling for answers, start dusting off old, purely theoretical ideas about time reversal on a quantum level. They whisper about how, in labs, they'd seen particles behave as if time was running backwards, but no one ever dreamed they'd see it happen to an entire person, let alone the entire human race. The initial bliss is intoxicating. 30 is no longer an endpoint to youth, but a new starting line. You won't grow old and frail. You'll grow young and vibrant. But the celebration doesn't last long. As the first wave of the reversed, the unaged, approach what would have been their 31st birthday, they are, instead, biologically 29 again. When they approach 32, they're 28. The miracle starts to feel tainted. A chilling realization dawns on everyone. This isn't a gift. It's a trade. You've traded the slow decline of old age for something far more terrifying. The complete and total erasure of your own existence. The New World Order, chronological 30s and 40s. The first decade of the reversal is pure, chaotic adaptation. Society, which has always been built on forward momentum, is thrown into a tailspin. Economies, structured around the ideas of growth and retirement, now face a workforce that will eventually become too young to be employable. The entire concept of a career is shattered. What's the point of climbing a corporate ladder when, in 20 years, you'll have the body and perceived maturity of a college kid? New industries explode overnight. Deceleration planning becomes the hottest new career, with financial advisors helping you front-load your earnings, saving frantically for a future where you can't work. Pension plans are now a relic, replaced by maturity trusts, funds you pour money into during your peak earning years, your chronological 30s, to be paid back to you when you're chronologically 60 but biologically a child. For you, this decade is a whirlwind. You're in the sweet spot, the period where your chronological age and biological age are still pretty close. You're 35, but you look and feel 25. You're in your physical prime, but with the added wisdom of a decade of life. It's a golden age, but it's poisoned by a constant, nagging anxiety. Every single decision is weighed against the countdown. Dating becomes a minefield of existential dread. You meet someone. You fall in love. You build a life. But you both carry the silent knowledge that this love has a different kind of expiration date. You won't grow old together. You'll grow young apart. A partnership of equals will one day become a caregiver and a dependent. Some couples, unable to face this, just embrace fleeting, intense romances. They live for the moment because the future is just too terrifying to think about. Others rush into marriage and parenthood, trying to cram a lifetime of milestones into the few years of normalcy they have left. And parenthood? That becomes the ultimate act of tragic hope. You have a child. For the first few years, it's almost normal. You're a young parent raising a small kid. But then a horrifying milestone arrives. Your child turns 10. Chronologically, you're 40. Biologically, you're 20. You look younger than you did on your wedding day. As your child is growing up and forming their own identity, you're starting to unlearn. It begins subtly. The complex software you mastered for work a few years ago now feels clunky. You forget advanced vocabulary, reaching for simpler words. It's the first, chilling whisper of what's to come. Your relationship with your own parents completely inverts. They're aging forward, moving into their 60s and 70s, growing frail in the traditional way. Meanwhile, you're getting stronger, faster, more youthful. They look at you with a mix of pride and a deep, inconsolable sadness. They're losing the adult child they knew, replaced by a stranger who looks like their child from a time long past but holds 30 years of memories they can't share. The generational gap becomes a chasm, an unbridgeable canyon of biological difference. The Great Inversion, chronological 50s and 60s. This is where the fabric of your life truly starts to unravel. At a chronological age of 50, you have the body of a 10-year-old. You celebrate your 50th birthday, a half-century of life in a body that hasn't even hit puberty. The world no longer sees you as an adult. Authority, respect, credibility, those are luxuries you can no longer afford. Imagine walking into a bank to discuss your maturity trust. You have 50 years of financial knowledge, a deep understanding of the market. But the person across the desk is a 25-year-old who just sees a child. They speak to you slowly, using simple terms. They ask if your parents are with you. The humiliation is a constant, grinding weight. Your career is long gone. By your mid-40s, you looked too young to be taken seriously. By 50, child labor laws, ironically, prevent you from holding any job at all. You are now completely economically dependent. Your life's work, the skills you spent decades honing, are trapped in a mind that's actively dismantling itself, all housed in a body that makes them useless. This is the era of unlearning. It's not just forgetting a few complex skills anymore. It's the active erosion of your identity. You, who were once a skilled architect, now stare at blueprints that look like an incomprehensible mess of lines. You remember the asterisk feeling of designing a building, but the specific knowledge, the load-bearing calculations, the material science has just evaporated. The process is terrifyingly systematic. The last things you learned are the first to go. Your mind is a library, and an invisible librarian is walking the stacks, pulling books from the shelves in reverse order and tossing them into a fire. Your relationships are almost unrecognizable. If your spouse stayed, the marriage has transformed. They are now in their 60s or 70s, aging, while you are a child. The romantic love, the partnership, has been necessarily replaced by a bond of care and responsibility. They are now your guardian. They dress you, they manage your affairs, they protect you. The intimacy is gone, replaced by a profound, heartbreaking tenderness. They remember the person they married, and they mourn you, even as you sit right in front of them. And your children. This is the deepest cut. They're now in their 30s. They're adults. They are you, 30 years ago. They have careers and families and worries of their own. And one of their biggest worries is you. You are their parent, but they are now your parent. They enroll you in special schools for the unaged, places where chronological adults in children's bodies can relearn basic skills. The conversations are surreal. Your 35-year-old son sits you down to talk about your behavior at school, looking at you with the same frustrated, loving expression you once gave him. You want to tell him about the day he was born, offer him advice on his marriage, share a memory from your own childhood. But the words get stuck. The memories are blurry, their emotional weight fading. You remember you love him, but the 50 years of context that gives that love its shape is disintegrating. He's becoming less your son and more just a kind, familiar man who takes care of you. The long goodbye, chronological 70s. By the time you're chronologically 70, you are biologically a toddler. You are what's left of a 70-year-old mind, locked inside the body of a 3-year-old. The world has now fully institutionalized the reversal. You live in a continuum care facility. A place that looks like a blend of a high-tech nursing home and a state-of-the-art preschool. Your life is a series of scheduled activities designed to manage your regression. There are memory sessions, where therapists use old photos and music not to jog your memory, but to provide comfort as it fades. They're documenting your decline, not fighting it. That fight was lost a long, long time ago. The unlearning is now catastrophic. You've unlearned how to read and write. Language itself is crumbling. You can still speak, but your sentences are simple, your grammar fractured. You're losing the words for complex ideas like government or sorrow. Your inner world, once a rich tapestry of experience and memory, is now reduced to a few primary colors: happy, sad, hungry, tired. Your spouse, now in their 80s or 90s if they're still alive, is a rare visitor. The journey is too hard, and the person they come to see is no longer there. They are a ghost, haunting the shell of a toddler. They hold your tiny hand, their wrinkled skin against your smooth skin, and tell you stories of your life together. You listen with a vague sense of pleasant confusion. You recognize their voice as a source of comfort, but the names and places mean nothing. It's like listening to a fairy tale. Your children, now in their 50s, are your primary connection to the world. They visit you. They bring you toys. They spoon feed you. And in their eyes, you see the most profound pain imaginable. They are mourning a parent who is still alive. The role reversal is absolute. They soothe your tantrums, they change your diapers, they make the heartbreaking decision of when to stop trying to explain who they are. One day, your daughter visits. She's 52 now. She shows you a photograph of you, her, and her brother, taken 40 years ago. In the photo, you are a strong man of 32, holding your children's hands. "That's you, Dad," she says, her voice thick with emotion. You look at the photo, then back at her face. You feel a flicker of something, a distant echo of recognition. You reach out your tiny hand and touch her cheek. A single word forms in your mind, a word you haven't used in years. You try to say it, but another word comes out. "Mama," you say. Her face crumples, and she finally lets herself weep for the father she has just lost forever. The return to zero. Chronological 80s and 90s. The final decade is a silent, gentle descent into nothingness. At a chronological age of 80, you're an infant. You have no language, no memories, no concept of self. You've unlearned everything: your name, the faces of your children, the feeling of love, the sting of loss. You are pure potential with no future. A beginning at the very end. You live in the final wing of the continuum care facility, the nursery ward. It's a quiet place, filled with cribs holding the silent, chronologically ancient. Nurses, trained in both geriatrics and neonatal care, move from crib to crib, feeding, changing, and holding their charges. They are the final witnesses to these unlived lives. Your existence is purely sensory. The warmth of a blanket. The soft melody of a lullaby. The taste of milk. There are no thoughts, only reactions. The 70 years of joy, pain, love, and failure that made up your life might as well have happened to someone else. The slate has been wiped clean. Your children, now old themselves, stop visiting. There's no point. The infant in the crib is not their father. It is a biological echo, a genetic vessel that the person they knew has long since departed. They sign the papers, they ensure the care is paid for, and they say their final goodbyes not to you, but to a memory. The final moments are quiet and clinical. Your body continues its backward journey, regressing from an infant to a newborn, then to a fetus. The biological processes that built you in the womb now meticulously dismantle you. On what would have been your 100th birthday, you reach the biological age of 0. And then, you simply cease to be. There's no flash of light, no final thought. Just the quiet, imperceptible click of a clock striking 0. The space you occupied is now empty. Your story, once written across a century, has been erased, letter by letter, until all that's left is a blank page. A life lived in reverse is not a life at all. It's an unwinding, a slow-motion theft of the self. To age is to accumulate memories, experiences, love, wisdom. It is the process of becoming. To unage is to have all of that stripped away, piece by piece, until you are rendered back into the raw material from which you were made. The world that embraced the reversal as a miracle learned a terrible lesson. A long life is not the same as a full life. The value of our existence isn't measured in the number of years we have, but in the direction we travel through them. It's the forward march of time, the building of a legacy, and the passing of knowledge to the next generation that gives our lives meaning. When that is reversed, life becomes a tragedy. You are a book being unread, a song being unplayed. You become a stranger to your own children and, ultimately, a mystery to yourself. You're given the gift of youth, but at the cost of your soul. And you learn, in the most brutal way imaginable, that it is far better to be an old person with a head full of memories than a young person with a future that has already happened. This story of a life in reverse makes you question the very nature of time and identity. So, I have to ask you, if you had the choice, would you take it? Would you trade the pains of growing old for the certainty of fading away? Let us know your thoughts in the comments below. And if this story made you think, make sure to like and subscribe for more explorations into the biggest what-ifs of our existence. What if time ran backwards? We remember the past, but not the future. We can break an egg, but we can't unbreak it. A ripple expands from a stone tossed in a pond, but it never shrinks back to where it started. It all feels like an undeniable, unbreakable law of the universe, a silent rhythm that governs every moment of our existence. The arrow of time, pointing from a fixed past to an open future, is the most fundamental experience we share. It's the canvas on which our lives are painted. But what if that rule was broken? What if, in a single, silent heartbeat, the entire universe hit rewind? What if every single thing, from the smallest particle vibrating in the void to the grandest galaxy spinning in the cosmos, started flowing backward? Imagine that tonight. Every shattered glass reassembling itself, every breath you exhaled sucking back into your lungs, every memory you made today unspooling in reverse. The smoke from a blown-out candle would gather itself from the air and retreat back into the wick. The ruins of ancient empires would rise from the dust, stone by stone, to stand pristine and new. But here's the real question, the one that truly gets under your skin: would you even notice? Together, we're going on a journey from the familiar world of cause and effect, down to the bizarre realm where physics says time has no direction, and then back out to the cosmic scale of a rewinding universe. We'll chase after the ultimate question. Is our own consciousness the only thing that truly feels time's arrow? This isn't just a thought experiment. It's a trip to the very edge of reality, and it might just change how you see every moment that comes next. The unseen rules of our world. Let's start with what feels certain. Our world is governed by an arrow. Not a physical one, but a rule so deep we build our entire lives around it. We call it the arrow of time. It's the steady march from yesterday, through today, and into tomorrow. It's the simple reason a cause always, without fail, comes before its effect. Think about it. You strike a match, then it bursts into flame. You hear the thunder after the lightning has already split the sky. You are born, you live, and you grow old. This sequence is the grammar of our universe. It's so intuitive that questioning it feels as absurd as questioning whether the ground is solid beneath your feet. This arrow is everywhere. It's in the smell of rain on dry earth diffusing through the air, never gathering itself back into the soil. It's in the slow decay of a sandcastle on the beach, as the wind and waves reclaim its towers and turn them back into smooth, anonymous sand. It's in the heat from your coffee cup warming the cool air in the room, never pulling that warmth back into the mug. This one-way street is what allows us to have memories, to learn, to grow. We collect experiences, building a personal history that shapes who we are and helps us guess what's next. Your identity is a story written in the ink of forward-moving time. Who you are today is a direct result of who you were yesterday, and all the days before that. We're so used to this flow that we rarely think about where it comes from. We just accept it, like gravity. It's the silent metronome of existence, ticking away behind everything, preventing the movie of our lives from suddenly playing in reverse. But this is where our journey really begins. Because scientists and philosophers have wrestled with a question for centuries. Is this arrow of time a real, fundamental law of nature? Or is it something else? An illusion? A statistical trick? A product of our own minds? What if I told you that when we zoom in, way past our everyday world, and look at the basic laws that write the code for our universe, this arrow just vanishes? What if, at the deepest level of reality, the universe doesn't actually care about the difference between past and future? To understand how time could run backward, we first have to understand why physics says it shouldn't have a favorite direction at all. The universe's secret symmetry. Picture a video of a perfect game of billiards. The break happens, and the balls scatter in a beautiful, complex dance. Classic cause and effect. Now, imagine you run the video in reverse. The scattered balls start to move, retracing their paths, uncolliding and unspinning until they miraculously reform into a perfect triangle, just as the cue ball rockets away from them. It looks like an impossible magic trick. But here's the amazing part. According to the laws of classical physics laid down by Isaac Newton, that reversed video is just as physically possible as the forward one. The laws themselves don't care which way time is flowing. This perfect indifference is called time reversal invariance or T-symmetry. This isn't just about billiard balls. This secret symmetry runs through an astonishing amount of fundamental physics. Take gravity. If you filmed Earth orbiting the Sun for a year and played it backward, you'd just see the Earth orbiting the Sun in the opposite direction. It would still follow the exact same path prescribed by Einstein's general relativity. Nothing in the math of gravity forbids this. Or let's go deeper, to electromagnetism, the force governing light and electricity. The beautiful equations of James Clerk Maxwell also have this T-symmetry. A radio wave traveling from a transmitter to your phone could, according to the laws, travel from your phone back to the transmitter. Even in the truly bizarre quantum realm, the foundational Schrödinger equation, which describes how particles evolve, is also time-symmetric. A particle's wave of probability, spreading out over time, could just as easily be described as converging back to a point. But physics is rarely that neat. It turns out there is a tiny crack in this perfect symmetry. In the strange world of the weak nuclear force, which governs certain types of radioactive decay, time's arrow does seem to matter. Experiments, like those at the Babar project in 2012, have actually demonstrated this. And this is the crucial part for the overwhelming majority of interactions that shape our world, from gravity to the light hitting your eye, the laws are two-sided. So we have a profound paradox. The macroscopic world we live in, the world of coffee, eggs, and memories, is relentlessly one way. Yet the fundamental laws of physics that build this world are almost perfectly two-way. It's as if the universe is a novel where every sentence is a palindrome, readable forwards and backward, but for some reason, we can only read it from front to back. If the basic rules don't enforce an arrow of time, where does it come from? The answer isn't a new force or law. It's found in a concept as simple as a messy room and as profound as the origin of the cosmos. The answer is entropy. The ghost in the machine. Entropy. If the laws of physics are a two-way street, why do we only see traffic moving in one direction? The reason is the second law of thermodynamics, and its star player: entropy. Entropy is often called disorder, and that's a good start. But more precisely, it's a measure of probability. It's the number of ways you can arrange the atoms in a system without changing what it looks like on a large scale. High entropy means there are tons of possible arrangements. Low entropy means there are very few. Think of a box with a divider. On one side, a gas of blue particles, on the other, red particles. This is a low entropy state. There's basically only one way to have all blue on the left and all red on the right. Now, pull out the divider. The particles mix into a purple haze. This is a high entropy state. Why? Because there are trillions upon trillions of ways to arrange the particles so they're mixed up, but still only one way for them to be perfectly separated. The system goes from ordered to disordered not because of some mysterious force pushing it to chaos, but simply because there are overwhelmingly more ways to be disordered. It's just statistics. This is why cream mixes into coffee but never unmixes. There are countless molecular arrangements for mixed coffee, but only a tiny few for separated cream and coffee. It's why a shattered glass doesn't reassemble. The state of shattered pieces on the floor has far more possible arrangements and thus much higher entropy than the single arrangement of whole glass on the table. But this created a problem. The 19th century physicist Ludwig Boltzmann, who pioneered this idea, realized that if the laws are reversible, then a movie of gas particles unmixing should be just as possible as a movie of them mixing. So why do we only ever see one version? The answer, physicists now believe, isn't in the laws, but in the universe's starting point. The arrow of time we experience is a side effect of our universe's history. The evidence strongly suggests that our universe began in a very, very special condition. The Big Bang was an event of unbelievably low entropy. Imagine the entire universe at its birth as a perfectly ordered cosmic egg. For the last 787 billion years or so, the universe has simply been doing the most statistically probable thing. It's been unwinding. It has been moving from that one, highly unlikely, low entropy starting point toward states of ever-increasing entropy. The expansion of the universe, the life and death of stars, the cooling of your coffee, all of it is part of this grand, cosmic trend. The thermodynamic arrow of time is this relentless march from order to disorder, from the improbable past to the probable future. This doesn't mean everything becomes a useless mess. On the way, pockets of incredible order can form, like life itself. A living thing is a fortress of low entropy complexity. But it only maintains that order by taking in low entropy energy, like food or sunlight, and spitting out high entropy waste, like heat, increasing the total entropy of the universe as a whole. Life doesn't break the second law. It surfs the wave of increasing entropy. So, time's arrow isn't something that happens to the universe. It is the unfolding of the universe itself. And if your mind is buzzing right now, and you're enjoying this trip into the nature of reality, consider subscribing to the channel. We ask questions like this every week, and subscribing is the best way to make sure you don't miss what's next. Now, let's break the rules. The Great Rewind. A universe in reverse. Okay, so our arrow of time is driven by the universe's journey from a low-entropy birth to a high-entropy future. So, what if that arrow were to flip? What if, right now, the universe started moving toward states of lower entropy? Let's imagine this from a godlike perspective, watching from outside. First, the expansion of space would grind to a halt and then, impossibly, reverse. Galaxies, now rushing away from us, would start rushing back. The great cosmic voids would shrink as galactic clusters converged on one another, a big crunch. Inside these galaxies, stars would do something even weirder. Instead of radiating light and heat, they'd start absorbing it. Faint, scattered light from across the cosmos would find its way back to stellar surfaces. Stars like our Sun wouldn't burn hydrogen into helium. Their helium cores would unfuse, turning back into hydrogen, getting hotter and smaller as they regressed. The beautiful, expanding clouds of supernova remnants would pull themselves back together, ending in a brilliant flash as they reformed into the giant stars that came before them. Here on Earth, it would be surreal. Heat would flow from cold things to hot things. An ice cube in a glass of water wouldn't melt. The water would get warmer as the ice cube grew, pulling heat from it. Rain would rise from the ground in streams to form clouds. Rivers would flow uphill from the sea. Decay and erosion would become forces of creation. Crumbled ruins would see their bricks and stones lift from the dirt and reassemble into pristine buildings. The pyramids would look younger by the minute. A forest fire would be a symphony of life, with smoke and ash flowing onto charred branches, which would then turn green as they pulled carbon dioxide from the air and turned it back into wood. From our outside view, it would all look like a movie playing backward. It's bizarre, but it's totally consistent with those time-symmetric laws of physics. The reversed motion of every atom is a valid solution. It's just a path that leads to a more ordered, lower entropy, and statistically freakish state. For this outside observer, it's a world where effects happen before their causes. The scattered billiard balls decide to form a triangle just before the cue ball hits them. A window becomes whole right before a baseball flies away from it. But this is all from the outside looking in. That's the easy part. The truly difficult question is the one we started with. What would it be like to be inside this rewinding universe? What would a conscious person actually experience? To answer that, we have to look inward. The mirror mind. Consciousness and memory. We've arrived at the heart of the paradox. You are inside the reversing universe. You're in your kitchen, looking at the shards of a broken glass on the floor. What happens next? Let's imagine two scenarios. In the first, the universe starts running backward, but your mind, your consciousness, and memory is somehow exempt and keeps moving forward. You'd witness a miracle. The shards of glass would vibrate, slide across the floor, fit together perfectly, and leap up onto the table, whole again. From your forward time perspective, this is an effect without a cause. You'd remember the glass being broken, and now it's fixed. A moment later, your friend might walk backward into the room and unspeak a sentence. Life would become a terrifying series of these impossible events. You would remember the future, that is, the state things were just in, and watch as the world moved away from it and into its past. Reality would be a nightmare. But this scenario assumes that your consciousness is somehow separate from the physical stuff of the universe. All of neuroscience tells us that's not the case. Your thoughts, your memories, your sense of self, it's all physical. It's patterns of electricity in your brain. Forming a memory is a physical process that increases the total entropy of the universe. So, let's consider the second, more likely scenario. If time reverses, it reverses for everything physical. That includes every neuron firing in your brain. So, what happens now? You're in the kitchen. The process we call seeing the glass reassemble begins. Photons travel from the reforming glass to your eyes and to your brain. But since your brain's processes are also reversed, you aren't forming a new memory of a reassembling glass. Instead, your brain is unforming the memory of the glass being broken. From your point of view, you wouldn't experience a miracle at all. You'd experience something that felt completely normal. Why? Because your psychological arrow of time, the very feeling of time passing, is generated by these physical brain processes. It too would flip its direction to match the new arrow of the universe. In this backward world, you would perceive the arrow of increasing entropy, which now points to what we call the past as the future. You would see the glass reassemble on the table and perceive it as a natural cause. And you would remember a future moment where you will knock it off the table. For you, causality would be perfectly preserved, just flipped. Waving goodbye would be the natural way to start a conversation. Growing younger would feel like the normal process of aging. You would never know time was running backward, because the very tool you use to measure time, your brain, is running backward too. The entire system is self-consistent. To its inhabitants, a backward universe would be completely indistinguishable from a forward one. They would discover their own second law of thermodynamics and identify their big crunch as a big bang, a low entropy beginning from which their universe unfolds. This leads to a stunning conclusion. The arrow of time might not be something we observe, but something our brain creates. The nature of you. This brings the giant, cosmic question of time down to the most personal level. The nature of you. If our feeling of time's flow is tied to the physical process of memory and entropy in our brains, what does that mean for our reality? It suggests that time as we feel it, this powerful river carrying us from past to future, isn't an external feature of the world. A rock doesn't experience time passing. Jupiter doesn't remember its last orbit. The concepts of past and future are meaningless to them. Only a system that can create and store information, like a brain, can make a distinction between before and after. In a very real sense, the arrow of time only exists for conscious observers. You aren't just a passenger on the river of time. Your consciousness may be the current that makes the river flow. You can feel this in how time seems to warp. When you're lost in a creative task, a flow state, hours can feel like minutes. Your internal clock just fades away. But in moments of intense fear, a few seconds can stretch into an eternity. In those moments, your brain is recording a massive amount of information, creating more frames of the event in your memory. When you play it back, the experience feels longer. Time isn't a rigid metronome. It's a flexible property of your conscious experience. So, if a reversed universe would feel normal, and our perception of time is a construction of our own minds, that raises one last, startling question. How do we know we aren't in a reversed universe right now? The answer is, we can't. If our universe is currently running backward toward its low entropy beginning, every memory, every history book, and every piece of scientific evidence would be perfectly aligned with that backward flow. We would remember being born from the grave and growing younger, destined for the womb, and we would call that life. We'd see stars absorbing light and call it fusion. We'd look at the converging galaxies and invent a theory of a Big Bang that started everything. From the inside, the experience would be seamless. The idea that time might actually be flowing forward toward a chaotic future would seem as ridiculous to us as an unbreaking egg seems now. The direction of time, in the end, might just be a matter of perspective. And our perspective is defined by the direction our minds happen to be making memories. We started with a simple fact. We remember the past, not the future. We found that at the deepest level, the laws of physics don't really share our obsession with that distinction. Our arrow of time seems to come from statistics, from the simple fact that our universe started in a highly ordered state and has been getting messier ever since. But the final twist came when we turned the lens on ourselves. We realized that if our minds are part of that same physical fabric, a universe flowing backward would feel just as normal as one flowing forward. Our psychological arrow of time would simply flip to match, and we'd be none the wiser. So, here's a final thought to carry with you. Are you really moving forward through time, from a past that is gone to a future that is yet to be? Or are you, right now, a traveler in a universe that is already rewinding, your memories seamlessly rewriting themselves every second to create the perfect illusion of progress? In the end, you would never know the difference. The hidden law of physics that unlocks time reversal. What if I told you the fundamental laws of our universe don't actually forbid time from flowing backward? That deep within the math that governs reality, from the silent waltz of distant galaxies to the frantic dance of the atoms in your own body, there lies a shocking secret. A hidden symmetry. One that suggests the past and future aren't as different as they seem, and that the unyielding march from yesterday to tomorrow might just be a stubborn, cosmic illusion. It's like watching a movie. We only ever see it play forward. But the information to play it in reverse is always there, stored on the film. So, why does our reality only seem to have a play button and not a rewind button? Why do we remember the past, but not the future? The answer, the key to this profound mystery, isn't some exotic, undiscovered force. It's a concept as fundamental as gravity and light, one that's famously misunderstood and gives time its direction. The answer lies in entropy. The grand illusion of time's arrow. Every moment of our lives points to the one-way nature of time. You can scramble an egg, but you can't unscramble it. You can watch a building crumble, but you'll never see a pile of dust spontaneously assemble itself into a skyscraper. A cup of coffee on the table will always grow cold. It will never draw heat from the room to get hot again. This is our lived experience. It's intuitive. It feels absolute. Physicists call this universal, one-way flow the arrow of time. British astronomer Sir Arthur Eddington coined the term in 1927, and it perfectly captures the asymmetry that separates the past from the future. The past is fixed, recorded in memory. The future is open, full of possibilities. The arrow flies in one direction, from an ordered, unbroken egg to the disordered chaos of a scrambled one. This seems so fundamental, we assume it must be encoded into the deepest laws of nature. We expect the equations that describe our world to have a built-in signpost that says, "This way to the future." But here's the secret. When we look at those laws, the signpost isn't there. At the most basic level, the laws of physics don't care which way time flows. Let's start with classical physics, the world of Isaac Newton. His laws of motion are the bedrock of our understanding of how things move. The most famous of these, F equals ma, is a perfect example of this hidden symmetry. Imagine you're watching a film of a ball thrown in a perfect, frictionless world. It rises, slows, hits the peak of its arc, and falls back down. Now, run that film in reverse. What do you see? The ball leaps from the hand, rises along the same path, slows to a stop, and falls back down. The reversed motion doesn't violate Newton's laws in any way. The equations of motion depend on time, the variable, t. If you replace t with negative t, the laws still work perfectly. The only thing that flips is the velocity. So, in the reversed film, the ball starts with an upward velocity instead of a downward one, but the forces acting on it, gravity, are unchanged. To the cold, impartial eyes of physics, both movies are equally valid. This isn't just for thrown balls. Imagine watching Jupiter orbit the Sun. Play the film backward, and you'd see Jupiter trace the exact same path, just in the opposite direction. Even Maxwell's equations, which govern electricity, magnetism, and light, share this profound symmetry. So, a paradox forms. Our daily experience screams that time is a one-way street. But the classical laws that govern everything we see tell us that, fundamentally, there's no difference between past and future. If the rules of the big world are time-symmetric, maybe the arrow of time comes from the strange and fuzzy rules of quantum mechanics? The quantum realm's bizarre time reversal. To find the source of time's arrow, we have to go small. This is the quantum world, where the master equation is the Schrödinger equation. It describes how a particle's state evolves through time. Surely, this must contain the secret of time's arrow. But when physicists looked, they found the opposite. Just like Newton's laws, the Schrödinger equation is also time reversal symmetric. An electron spinning in a magnetic field, if you reversed its evolution, would trace a perfectly valid path back to where it started. However, reversing time here is far stranger than just running the movie backward. It's not just swapping t for t. Nobel laureate Eugene Wigner figured out that to make the Schrödinger equation work in reverse, you have to do two things. Flip the direction of time, and take the complex conjugate of the particle's wave function. This is where things get weird. A wave function includes imaginary numbers. Taking the complex conjugate is like flipping the sign of the imaginary parts. So, quantum time reversal means you don't just rewind the motion. You also invert a fundamental aspect of the particle's internal state. It's like rewinding a movie and, at the same time, flipping the film to its mirror image. This complex symmetry connects to one of the most successful ideas in particle physics: CPT symmetry. Captain stands for charge, parity, and time. It's a theorem, a cornerstone of modern physics that has held up to every test, which states that if you perform 3 transformations on any physical system, the resulting system will obey the exact same laws of physics. The 3 transformations are: 1. Charge conjugation, C**. Swap every particle with its antiparticle. 2. Parity transformation, P**. Reflect the system in a mirror. 3. Time reversal, T**. Run time backward. The Captain principle says our universe and a mirror universe, with all antimatter, everything spatially inverted, and time running backward would be indistinguishable in terms of the physical laws they follow. This has a bizarre consequence. Physicists have found that some particle interactions violate CP symmetry on its own. But if the overall Captain symmetry must be conserved, a violation of CP must imply a corresponding violation of T, time reversal symmetry, to keep the cosmic books balanced. And yet, this is a subtle effect, only seen in the decay of exotic particles. It doesn't seem powerful enough to explain why coffee cups don't reassemble themselves. The mystery has only deepened. We've looked at the grand laws of motion and the intricate rules of the quantum world, and everywhere we've found that the laws of physics are ambivalent about the direction of time. So if the fundamental laws don't create the arrow of time, where does it come from? The reason for time's unyielding arrow is not a law of motion, but a law of probability. It is the relentless second law of thermodynamics. Entropy, the universe's one-way street. The secret to time's arrow isn't in a single particle, but in the collective behavior of trillions of them. It's a principle born from steam engines, not particle accelerators. It is the law of entropy. What is entropy? It's often called a measure of disorder, but a better way to think about it is as a measure of probability. The second law of thermodynamics states that in an isolated system, entropy will always tend to increase over time. Systems naturally go from order to disorder, simply because disorder is vastly more probable. Think of a sandcastle. That's a highly ordered, low-entropy state. A wave washes it away, leaving a shapeless, high-entropy mound of sand. Why? Because there's only one way for those sand grains to be your specific sandcastle, but there are a near infinite number of ways for them to be a messy pile. The universe, just by playing the odds, moves toward the state with the most possible arrangements. It moves toward chaos. This is the heart of the arrow of time. When a glass shatters, it's not that physics forbids the pieces from flying back together. The problem is probability. For the glass to reassemble, trillions of atoms would all have to move with the exact, perfectly coordinated velocities in reverse. The number of ways for the glass to be in a shattered, high-entropy state is incomprehensibly larger than the one way for it to be in a whole, low-entropy state. The universe doesn't forbid miracles. It just makes them so improbable they might as well be impossible. The one-way flow of time we experience is simply the universe moving from less probable states to more probable states. That's the secret. But this raises a deeper question. If the universe is always moving toward higher entropy, that must mean that in the past, it was in a state of much lower entropy. For us to experience an arrow of time at all, the universe must have started in a state of extraordinary, almost unbelievable order. And this is precisely what our cosmological observations tell us. This idea is known as the past hypothesis. It posits that the Big Bang, the beginning of our universe 8 billion years ago, was an event of unbelievably low entropy. This feels counterintuitive. We picture the Big Bang as a hot, chaotic explosion. But in the language of thermodynamics and gravity, a hot, dense, perfectly smooth soup of particles, what the early universe was like is actually a state of incredibly low entropy. The reason is gravity. For a box of gas, the high entropy state is when the gas is spread out. But for a system dominated by gravity, the opposite is true. A smooth, uniform distribution of matter is like a pencil balanced on its tip, unstable and highly ordered. The high entropy, most probable state is for everything to be clumped together into black holes. The universe did not start out full of black holes. It started with the pencil perfectly balanced. Since that moment, the pencil has been falling. The universe has been evolving from that initial low-entropy state, with gravity pulling matter together into galaxies, stars, and planets. Stars are entropy-generating machines, turning low-entropy fuel into heavier elements and releasing disordered heat and light. The arrow of time that governs our lives is the echo of the Big Bang. We are living in the unfolding consequences of the universe's highly ordered birth. This understanding is a huge shift in perspective. It suggests time's arrow isn't absolute but a feature of our particular cosmic neighborhood. And it leads to a tantalizing question. If the arrow of time is just a matter of overwhelming probability, could we, in a small, isolated system, make time run backward? For decades, this was pure science fiction. Until it wasn't. The breakthrough and its mind-bending implications. The theory was settled. Fundamental laws allow time reversal, but the second law of thermodynamics makes it practically impossible. But what if you could control every single piece? What if you could give every atom the precise kick it needed to reverse its journey? This is what a team of physicists from Russia and the United States announced they had achieved in March of 2019. They didn't build a time machine. They used a quantum computer to, for a fleeting moment, reverse the arrow of time for a tiny quantum system. Led by Dr. Gordy Lasovic, the team used IBM's public quantum computer. Their experiment was a quantum version of a break shot in pool. They started with their quantum bits, or qubits, in a highly ordered, low-entropy state. Then, they let the system evolve. The quantum information of the qubits spread out, becoming more complex and disordered, the quantum equivalent of entropy increasing. It was time flowing forward, from order to chaos. Then came the crucial step. They ran a special algorithm that acted as a time reversal mirror, giving the system a perfectly calculated kick to reverse its evolution. And it worked. The quantum computer's state evolved backward, from chaos back to order. For a fraction of a second, the arrow of time had been reversed. As Dr. Lasovic put it, we have artificially created a state that evolves in a direction opposite to that of the thermodynamic arrow of time. But the results also confirmed why this never happens in our daily lives. The experiment was successful about 85% of the time with a simple 2-qubit system. When they added a third qubit, the success rate plummeted to around 50%. The more complex the system, the more impossibly difficult it becomes to perfectly reverse its evolution. The experiment didn't break the second law. It confirmed why the law is so powerful by showing just how much precise effort is required to overcome it, even on a tiny scale. The philosophical implications are what truly boggle the mind. If the past and future are just labels for different directions and the laws of physics are indifferent, it lends support to a fascinating model of reality: the block universe. This theory suggests that time isn't a flow, but a landscape. All of time, every moment of the past, present, and future exists simultaneously, just like all of space exists. Our consciousness, bound by the arrow of entropy, simply moves through this four-dimensional block, experiencing it slice by slice. In this view, the future is already written. We just aren't far enough along the track to read it yet. We started with a simple question. Why does time only move in one direction? We've discovered that the laws of physics, in their deepest form, are time-symmetric. They don't have a preferred direction for time's arrow. That arrow is an emergent property, a consequence of living in a universe that began in an extraordinarily low entropy state. The relentless march from order to chaos is simply the universe playing the odds. The 2019 quantum computer experiment was a landmark achievement, a fleeting moment where humanity managed to bend that arrow back on itself, proving that the one-way street of time has a hidden U-turn. It leaves us with one last, profound thought. If our sense of time's flow is merely a product of increasing entropy, and our own brains are entropy-generating machines, is our perception of past, present, and future an illusion? Are we just travelers on a fixed path through a static block of space-time, with our memories painting a picture of where we've been, and the fog of probability obscuring the road ahead? Is the river of time truly flowing, or are we simply flowing down the river? If this journey into the nature of time has bent your perception of reality, let us know what you think in the comments below. Is time an illusion? And if you want to continue exploring the biggest questions in physics, make sure to subscribe and ring that notification bell so you never miss an expedition into the unknown. The cosmic law that forces time forward. Why doesn't a shattered glass ever leap from the floor and reassemble itself in your hand? Why can't a scrambled egg reverse its journey, pulling itself from the pan, back into a perfect, unbroken shell? We know, instinctively, that it's impossible. It feels like it violates some deep, unspoken rule. But what is that rule? The answer isn't just about the egg or the glass. It's a cosmic law, a secret the universe has held since its very first moments. This secret is what locks time into a forward march, the reason yesterday is a memory and not a destination. It's the story of how everything we experience, from our coffee cooling to our memories forming, is just an echo of the Big Bang. Let's uncover the one cosmic condition that forces time forward and prevents our past from ever becoming our future. The apparent rules of time's arrow. our lives are lived on an invisible, one-way street we call time. It's maybe the most fundamental part of our existence. We're born, we get older, we remember what happened, and we plan for what's next. This forward march feels as real and unyielding as gravity. The British astrophysicist Arthur Eddington gave it a name back in 1927, the arrow of time. It's a concept that just feels right, woven into the fabric of every single moment. Think about the simple, irreversible things that define our days. You pour cream into your coffee, and it blossoms into elegant clouds before melting into a uniform tan. You'll never see that spontaneously reverse, the cream neatly separating itself back out. A drop of ink in a glass of water diffuses, its color spreading until the whole glass is a faint, consistent shade. The ink will never gather itself back into a single, perfect droplet. A log burns in a fireplace, turning to ash and smoke, releasing heat and light. No matter how long you wait, that ash and smoke won't recombine, pulling heat from the room to magically remake the log. These are all examples of the thermodynamic arrow of time, one of several arrows physicists talk about. It's dictated by one of the most powerful laws in physics, the second law of thermodynamics. Simply put, this law says that in an isolated system, things tend to go from a state of order to disorder. The whole egg is ordered. The scrambled egg is disordered. The log is an ordered structure. The ash and smoke are a disordered mess. In every case, nature relentlessly moves toward the more disordered state. This arrow isn't just physical, it's also deeply psychological. We have a powerful psychological arrow of time. We remember the past, but we have no memories of the future. Yesterday's events feel fixed, recorded, and accessible to our minds. Tomorrow is a land of possibilities, of unknowns we can guess at, but never truly remember. We feel like our actions can change the future, but the past is untouchable. This one-way street of memory and influence gives us our personal feeling of time's flow. We are creatures built to see time moving from a known past to an unknown future. There's also a cosmological arrow of time. When we look out at the universe, we see that it's expanding. Galaxies are, on average, moving away from each other. The space between them is stretching. This expansion points in a clear direction from a smaller, denser, hotter past to a larger, more spread out, and cooler future. This direction of expansion is another one of time's arrows, and as we'll see, it's deeply connected to all the others. So, the evidence is all around us. A broken cup stays broken. A memory only forms in one direction. The universe itself gets bigger. Everything in our experience screams that time is a one-way street. It flows from past to future, from order to disorder, from cause to effect. This seems like the obvious rule of our reality. It's so obvious, we rarely even think to question it. But what if I told you that when we zoom in, way down to the fundamental building blocks of the universe, this obvious, one-way rule completely disappears? What if the laws governing the dance of atoms and particles don't have any preference for past or future at all? This is where our story gets really interesting. This is the hidden contradiction at the heart of reality, a puzzle that forces us to look back to the very beginning of the universe for the answer. The hidden contradiction. The arrow of time feels absolute, doesn't it? A universal truth. Yet, when we peer into the deepest level of reality that physics can describe, we find something unsettling. Something that seems to fly in the face of our everyday experience. The fundamental laws of physics, for the most part, don't have an arrow of time. They are, as physicists say, time-symmetric. What does that mean? It means the equations that describe how the universe's most basic pieces behave work perfectly well whether you run time forwards or backwards. Imagine filming two billiard balls colliding on a frictionless table. You watch the white ball hit the red one, sending them both scattering. Now, imagine you play that video in reverse. The scattered balls travel back along their paths, collide, and the white ball continues on its way, moving backward. Does the reversed video look impossible? Not at all. It looks just as plausible as the forward version. The laws of motion governing that collision in this case, Newton's laws, are time reversible. The math doesn't care which way time is flowing. This isn't just true for billiard balls. It holds for the vast majority of the laws of the universe. The equations of gravity that describe a planet orbiting a star work just as well for a planet orbiting the other way. Maxwell's equations for electricity and magnetism work for light waves that radiate outwards from a source, but they also have solutions for waves that converge perfectly onto a source. Even in the bizarre world of quantum mechanics, the main equation describing how a quantum system changes, the Schrödinger equation, is time reversible. So here's the profound contradiction. The big world we live in is ruled by irreversible processes. Eggs break, cream mixes, people age. That's the arrow of time. But the microscopic world of particles, governed by the fundamental laws of physics, is almost entirely reversible. The laws themselves don't distinguish between past and future. This is the central mystery that has puzzled physicists for over a century. If the basic rules of the game are time symmetric, where does the arrow of time come from? Why does the universe as a whole, and everything in it, so clearly prefer one direction? If the microscopic world is a two-way street, why is the macroscopic world a one-way highway? It can't be some new law that only applies to big things. After all, big things are just made of small things. An egg is just a collection of atoms. A cup of coffee is just a collection of atoms. We are just collections of atoms. And those atoms are all following the same time-symmetric rules. Somehow, when you put enough of these time-symmetric building blocks together, a direction for time just appears. This puzzle suggests that the arrow of time isn't a fundamental property of time itself. It's not built into the universe's clockwork. Instead, it must be what physicists call an asterisk emergent property. It emerges from something else. But what? The secret to why time moves forward isn't in the rules of physics, but in a single, extraordinary fact about how the universe started. It lies in a state of impossible order, present at the very beginning of time. Unveiling the secret. The law of increasing entropy. To solve the puzzle of time's arrow, we need to go back to that idea we touched on earlier. The second law of thermodynamics. This law introduces one of the most important concepts in all of science, entropy. Put simply, the second law says that the total entropy of an isolated system can never decrease. For any real-world, irreversible process, the total entropy will always increase. This relentless increase of entropy is the very thing that gives us the thermodynamic arrow of time. So, what is entropy? The common shortcut is to call it disorder or chaos. A scrambled egg is more disordered than a whole egg, so it has higher entropy. A messy room is more disordered than a tidy one, so it has higher entropy. This is a good starting point, but the real meaning of entropy is more subtle and way more profound. The idea was first developed in the 1850s by physicist Rudolf Clausius, who was studying steam engines. He noticed a basic asymmetry in nature. Heat always flows on its own from a hotter object to a colder one, and never the other way around. Clausius came up with the term entropy to quantify this one-way flow of energy. But it was another physicist, Ludwig Boltzmann, who gave entropy its deeper, statistical meaning. Boltzmann's insight was revolutionary. He realized that the big-picture properties we see, like temperature and pressure, are really just the collective, statistical behavior of a huge number of tiny particles, or atoms. Boltzmann connected entropy to the number of ways you can arrange the microscopic parts of a system without changing how it looks on a large scale. A system's entropy is a measure of the number of possible microscopic arrangements or microstates that all correspond to the same macroscopic state or macrostate that we actually see. Let's use an analogy. Imagine a new deck of 52 cards. There's only one way to arrange them in perfect, new deck, order. This is a very specific, highly ordered arrangement. Because there's only one microstate, the specific card order, that corresponds to the macrostate of perfectly ordered. This state has very low entropy. Now, shuffle the deck. What are the odds you'll shuffle it back into that one perfect order? Basically zero. Instead, you'll get some jumbled mess. But here's the key. There are an astronomical number of ways for the deck to be jumbled. We can think of all of these messy arrangements as belonging to the same macrostate, shuffled. Because there are so many different microscopic arrangements that all look like a shuffled deck, this macrostate has incredibly high entropy. The second law of thermodynamics is, at its heart, a law of statistics. When you shuffle a deck, you're overwhelmingly likely to go from the single low entropy state to one of the countless high entropy states, simply because there are vastly more of them. It's not forbidden for the cards to shuffle themselves into perfect order. It's just mind-bogglingly improbable. The same principle applies to everything. The air molecules in your room are spread out more or less evenly. This is a high entropy state. There are a staggering number of ways to arrange the individual molecules that all result in air filling the room. What are the chances that all the air molecules will spontaneously rush into one corner? The number of microstates for that arrangement is tiny in comparison. So, it never happens. The system naturally moves toward the state with the most possible arrangements. It evolves toward maximum entropy. This is the real reason cream mixes with coffee. There are very few low-entropy states where the cream and coffee molecules are separate. But there are a near infinite number of ways for them to be mixed together in a high-entropy state. The universe simply proceeds toward the most probable state. The scrambled egg, with its proteins all tangled up in countless ways, is a far more probable state than the highly structured proteins in an unbroken egg. Now, we can finally unveil the cosmic secret. The arrow of time exists for one simple reason. Our universe began in a state of extraordinarily low entropy. At the moment of the Big Bang, the universe was an incredibly hot, dense, and crucially smooth soup of particles and energy. This uniformity, this smoothness, was a state of incredibly low entropy. It was like the entire cosmic deck of cards starting out in perfect, unshuffled order. This special initial condition is often called the past hypothesis. That's the secret. It's not a law of physics that creates the arrow of time. It's an initial condition. The laws are symmetric, but the starting point was not. The universe was handed a perfectly ordered deck, and ever since, it has been shuffling it. The inevitable consequence. The universe began with a secret, a state of impossible order. That single fact unlocks the mystery of time. Because the universe started in such an exceptionally low entropy state, it had nowhere to go but toward more entropy. It was wound up like a cosmic clock, and for the past 13.8 billion years, it's been unwinding. This relentless, one-way journey from order to disorder, from low entropy to high entropy, is the arrow of time. It's not that time itself is fundamentally flowing one way. It's that the asterisk state of the universe is evolving one way from an incredibly improbable, special past to a much more probable, generic future. We perceive this evolution as the flow of time. The past is the past because it was a time of lower entropy. The future is the future because it will be a time of higher entropy. This explains the thermodynamic arrow, but what about the others? Well, they all seem to fall into place as consequences of this master arrow. Consider the psychological arrow of time, the fact we remember the past and not the future. The leading explanation connects this directly to entropy. Forming a memory is a physical process in the brain. It involves creating new, ordered neural connections. To do this, your brain consumes energy and radiates waste heat, increasing the total entropy of the universe. You can only create an ordered record of an event, a memory, in a universe that allows for an overall increase in entropy. We remember the past because the past is the direction of lower entropy. We can't remember the future because the universe hasn't produced the higher entropy states that will define it yet. Now, what about the cosmological arrow, the expansion of the universe? This might seem like a paradox at first. The early universe was a smooth, uniform soup, which sounds disordered. Today's universe is lumpy, with galaxies and stars, which sounds more ordered. So how has entropy increased? This is where gravity becomes the star of the show. In a system dominated by gravity, a smooth, uniform distribution of matter is actually a state of low entropy. A clumpy distribution is a state of high entropy. Gravity wants to pull things together. A uniform gas is an ordered state because all that matter could fall together, but hasn't yet. As the universe expands, gravity pulls matter into clumps, forming stars and galaxies. This process of clumping dramatically increases the entropy of the universe. The cosmological arrow and the thermodynamic arrow point in the same direction, away from that special, smooth beginning. We can even see this in the way light works. The reason a star radiates light outwards, rather than sucking light inwards, is also tied to entropy. An expanding sphere of light is a much more probable, higher entropy configuration than a perfectly synchronized sphere of light converging on a single point. The latter would require an incredibly fine-tuned starting arrangement, which is entropically forbidden. The universe makes ripples that spread out, not ripples that converge from the edges to make a splash in the middle. All the arrows of time we see are aligned. They all point the same way, away from the past and toward the future. And they all point that way for the same reason. They are consequences of the universe starting in a state of incredibly low entropy. The forward march of time is the inevitable result of the universe's secret, highly ordered birth. It's the echo of the Big Bang, playing out in every moment of our lives. The deepest mystery. Why the secret? So, we've uncovered the secret. Time moves forward because the universe began in an incredibly special, low-entropy state. But, as often happens in science, solving one mystery just reveals a deeper one. The question is no longer, where does the arrow of time come from? The question is now, why did the universe begin in such an improbable, low-entropy state? If you were to randomly pick a state for the early universe, you'd almost certainly pick a high-entropy one, a chaotic, lumpy mess. The smooth, ordered state our universe started in is, statistically speaking, bafflingly unlikely. Why was our universe born so special? This is one of the deepest questions in all of cosmology. Our best current guess lies in a theory called cosmic inflation. Inflation suggests that in the very first fraction of a second after the Big Bang, the universe went through a period of hyper-accelerated, exponential expansion. In a flash, a region of space smaller than a proton was stretched to a size larger than our entire observable universe. This incredible stretching would have acted like a cosmic steamroller. Any initial wrinkles or chaos would have been smoothed out over vast distances. Inflation would have taken almost any starting conditions and stretched them into the incredibly smooth, uniform, low-entropy state that the arrow of time requires. It doesn't fully explain why inflation happened, but it gives us a plausible story for how the special state came to be. This brings us to even wilder territory. Could the universe one day collapse back on itself in a big crunch? And if it did, would time reverse? Stephen Hawking famously wondered about this. At first, he thought that in a collapsing universe, the arrow of time might flip and entropy would start to decrease. But he later changed his mind. More advanced models suggest that this wouldn't happen. Entropy would likely continue to increase even as the universe crunched back down. A collapsing universe would not be a film of our universe played in reverse. But a big crunch seems unlikely anyway. Our best observations suggest the universe's expansion is accelerating, driven by a mysterious force called dark energy. If this keeps up, the universe is headed for a very different fate. Not a fiery crunch, but a cold, quiet end known as the heat death. This is the ultimate consequence of the second law of thermodynamics. Over trillions and trillions of years, the universe will keep expanding and cooling. Stars will burn out. Galaxies will go dark. Even black holes will eventually evaporate. The universe will approach a state of maximum entropy, a vast, cold, dark, and perfectly uniform soup of stray particles and radiation. There will be no temperature differences left to drive anything. No work can be done. No complex structures can exist. No new memories can be formed. In a state of heat death, the arrow of time will, in a sense, stop having any meaning. When everything is in a state of perfect, random balance, there is no more, before, and after. The cosmic clock will have fully unwound, and time's forward march will come to a silent, motionless end. The flow of time, that most intimate feature of our reality, isn't a fundamental law written into the cosmos. It's a consequence. An echo. It is the long, fading reverberation of the universe's birth. We've seen that the deepest rules of physics don't have a direction, but the game clearly does. The solution wasn't in the rules, but in the starting position. The universe began with a state of profound, improbable order. A low entropy beginning. Because of that one special condition, the universe has been on a one-way journey ever since. It has been falling from order into disorder, from low entropy to high entropy. That journey is the arrow of time. It's why cream mixes into coffee and why we remember the past but not the future. Our entire existence, every thought we have, is powered by this cosmic unwinding. We are all just riding the relentless wave of increasing entropy that began 13.8 billion years ago. And yet, the final mystery remains, pushing us to the absolute limits of science. Why? Why did the universe begin with this secret? Why was it born in that exquisitely ordered state, ready to begin its long roll downhill? Was it a random fluke? A necessity of some deeper law we haven't found yet? Or is it something we may never have the capacity to understand? That is a question that echoes from the dawn of time itself, and it remains one of the deepest and most tantalizing questions in all of science. If you enjoyed this trip to the heart of time, consider subscribing and sharing this video. And let us know in the comments, what other cosmic mysteries would you like us to explore next? I watched a star unburn itself from existence. You've seen stars burn out. Maybe through a telescope, or in a planetarium, or just in the deep recesses of your imagination. A flicker, a fade, a final breath before the long, cold dark. But have you ever seen one unburn? I have. I watched a star pull its fire back from the darkness, shrink from a giant into a tiny seed of light, and then vanish as if it were never there. This isn't a story about death. It's a story about erasure. This is a journey to a place where the universe isn't just dying. It's slowly, beautifully, erasing itself. A place where time doesn't heal all wounds, it undoes them, stitch by painstaking stitch, until the wound was never even inflicted. What I saw defies every intuition we have. It challenges the very idea of cause and effect. It suggests that the most fundamental rule of our cosmos, that things fall apart, might only be half the story. So, come with me, back to that impossible corner of reality. Let's watch, together, as a star is born from its own grave. Let's witness the cosmos methodically, beautifully, unmaking itself. The anchor to reality. In our world, the universe plays by a simple, unbreakable rule. It's a rule you feel in your bones, even if you don't know its name. It's why a shattered egg never leaps off the floor to reassemble itself. It's why cream stirred into coffee never separates back into a perfect white swirl. It's why the smoke from a blown-out candle never flows back to the wick. This principle is the second law of thermodynamics, and it gives us what we call the arrow of time. This arrow points in only one direction, from order to disorder. From a perfect sandcastle to a windswept mound. From a hot, concentrated star to a diffuse, cooling nebula. Scientists call this disorder entropy, and in our universe, entropy always increases. Think of it as the universe's commitment to messiness. Every single moment, every interaction, every fusion reaction in the heart of a star adds to this relentless march toward cosmic chaos. In our world, stars are born from collapsing clouds of gas and dust, pulled together by gravity. They ignite, burn for billions of years, and then they die. For a star like our Sun, this death is a pretty gentle affair. After it runs out of hydrogen, it'll swell into a red giant, shed its outer layers as a gorgeous planetary nebula, and leave behind a cooling, dense core called a white dwarf. For stars much bigger than our Sun, the end is way more spectacular. When their fuel is gone, the crushing force of their own gravity makes them collapse violently, triggering a cataclysmic explosion we call a supernova. This blast is one of the most powerful events in the universe, briefly outshining an entire galaxy and forging the heavy elements that make up planets, and even you and me. This is the life cycle we know. Birth, life, death. An explosion of light and energy that fades over eons. This is the story written by the forward arrow of time. A story of things breaking down, of energy spreading out, of order giving way to chaos. It is the fundamental direction of our reality. But where I went, that arrow is flipped. The rules are inverted. There, the universe doesn't remember chaos, it remembers order. It isn't a journey toward a cold, dark end, but a meticulous retreat toward a hot, dense beginning. The unburning. A star undone. Imagine floating in a silent, crystalline void. The darkness is absolute, but it doesn't feel empty. It feels expectant. Your eyes adjust not to a lack of light, but to a asterisk reversal of it. Instead of distant stars twinkling, you see points of blackness that seem to be gathering. Tendrils of faint, ghostly light, like cosmic spiderwebs, aren't expanding outward from a source, but are being drawn inward. Photons, the very particles of light, are on a return journey, retracing their long paths across the cosmos to converge on a single, shrinking point. This is how it begins. Not with a bang, but with a silent, relentless gathering. I watched one such point, a phantom in the dark. It was the ghost of a star that, in our timeline, would have been a red giant. Here, it was a vast, diffuse sphere of cooling gas. But it wasn't cooling. It was doing the opposite. The light it had spent eons casting out was now coming home, feeding back into its surface. The star was getting smaller, brighter, and hotter. Layer by once expelled layer, the star began to reassemble itself. A planetary nebula, which in our universe is the beautiful, expanding shroud of a dying star, was here a contracting halo. Wisps of ionized gas, looking like cosmic butterflies or celestial eyes, were folding in on themselves. The gas was being pulled back, as if by an invisible thread, rejoining the star's shrinking atmosphere. The star wasn't shedding its skin. It was putting it back on. With every moment, the star grew more defined. Its color shifted from a dull, angry red to a vibrant orange, then to a brilliant, incandescent yellow-white, just like our own sun in its prime. It was passing through its main sequence, but backward. But what about its core? In a star like our Sun, the core is a furnace burning at 15 million degrees Celsius, where hydrogen nuclei are smashed together to make helium. That's fusion. But here, in this backward star, it was as if this elegant process was running in reverse. Instead of creating helium-4, the core was systematically dismantling it. It was a reverse proton-proton chain. Helium-4 nuclei absorbed energy and split apart. Reactions that once released massive amounts of energy now absorbed it. The core, instead of being a roaring furnace pushing outward, was a cryptic heat sink, pulling energy inward. Gravity, no longer fought by the pressure of fusion, was winning a slow, silent victory. The star shrank because the very engine that held it up was methodically taking it apart. For much bigger stars, the process is even more dramatic. In our universe, massive stars use carbon, nitrogen, and oxygen as catalysts to fuse hydrogen into helium in what's called the CNO cycle. In this reversed world, the CNO cycle would also run backward, using energy to break helium apart. The turbulent, churning layers of these massive stars would grow still. Each layer would settle, cool, and contract as the unfusion engine at its heart consumed the star's heat. And so, I watched this star shrink. It pulled back its light, its heat, its very presence. It passed backward through its life stages, from a stable yellow star to a contracting protostar. The glowing ball of gas became dimmer and cooler until the internal reactions stopped entirely. Gravity continued to pull the now inactive cloud inward, but instead of igniting, it simply grew denser and darker. Eventually, the star was no longer a star. It had become what it once was: a vast, dark cloud of hydrogen and helium. It had unburned itself, not into a corpse, but back into a cradle. A star had been erased from the sky. The solar system in retreat. The star's reversal wasn't happening in isolation. Its retreat sent ripples or maybe anti-ripples through its entire system. The planets, which had followed predictable orbits for eons, were now hostages to a clock winding backward. Their story was no longer one of formation, but of dissolution. Picture a world like our own Earth. In this reverse timeline, its destiny is to unbecome. The first thing to go would be the light. As the star cooled and shrank, the sunlight bathing the planet would dim into a perpetual twilight, and then fade into a deep, unending dusk. Photosynthesis, the process that powers most life, would fail. Plants would begin to break down, releasing their stored energy, their complex molecules disassembling into simpler ones. Life itself would run backward. Creatures wouldn't be born, grow old, and die. They would rise from their graves, grow younger, and return to the womb. Geologically, the planet would deconstruct itself. Oceans would freeze over, and then that ice would retreat, not by melting, but by turning back into gas and being drawn into the crust. Plate tectonics would reverse. Mountains would rise from sediment as continents unstuck themselves. Volcanoes would inhale their own plumes of ash, their lava flows creeping back up their slopes. As the star's mass decreased through unfusion, its gravitational pull would weaken. This means the planet's orbits would begin to spiral outward. The delicate gravitational dance holding the solar system together would unwind. Moons would recede from their planets, drifting back into their own lonely orbits. Asteroids and comets once captured by the star's gravity would be set free. The asteroid belt would see its inhabitants drift away, back into the interstellar deep. Comets, their tails of ice and dust now pointing toward the shrinking star, would have that material refreeze onto their surfaces before they broke free entirely. Eventually, the planets themselves would begin to disintegrate. Their atmospheres would be stripped away. The very rocks and metals that formed them would break apart. The process of accretion, where small bits clumped together to form planets, would run in reverse. The planets would crumble, first into a swarm of boulders, then a disk of dust, and finally into a diffuse, cold ring of particles orbiting a dark, cold protostar. The entire solar system, once a complex and dynamic machine, would be reduced to its primordial state, a vast, featureless cloud of cold gas and dust. Just as the star had unmade itself, so too had it unmade its family. The memory of a solar system, wiped clean. The unwinding galaxy. Zoom out from the ghost of that solar system, and an even more profound reversal comes into view. The galaxy itself, a swirling city of billions of stars, is also caught in this backward flow. A spiral galaxy like our Milky Way isn't static. It's a dynamic system shaped by gravity and star formation. In a reverse time universe, this entire cosmic history unwinds. Imagine looking at a spiral galaxy from above. In our universe, its arms are stellar nurseries, full of bright, young, blue stars. But here, the arms are places of collection. Mature stars drift back into the arms, which appear to be unwinding, like smoke being drawn back into a fire. The galaxy isn't aging and getting redder. It's growing younger and bluer. It's like watching a photograph slowly developing in reverse. Galactic collisions become elegant, impossible ballets. In our universe, when two galaxies merge, gravity tears them apart into a new, larger, more chaotic galaxy. Here, we'd witness the opposite. A big, disordered elliptical galaxy would begin to organize itself. Streams of stars would flow back toward the main body. Then, with breathtaking slowness, the single mass would split into two distinct, well-ordered spiral galaxies, which would then drift gracefully apart as if they'd never met. At the heart of most galaxies, including ours, lies a supermassive black hole. In our universe, these monsters grow by consuming anything that gets too close. They're surrounded by incandescent whirlpools of matter called accretion disks. But in the reverse universe, these monsters aren't feeding. They are, in a sense, vomiting matter back into existence. The accretion disk spirals outward. Gas and dust cool as they move away from the black hole. Instead of being engines of consumption, black holes become fountains of creation. This isn't just theory. It's a literal movie of a black hole played backward. As we pull back even further, we see the entire structure of the cosmos changing. Galaxy clusters, vast gravitationally bound assemblies, are dissolving. Galaxies are drifting apart, escaping the cluster's pull. And on the largest scales, the universe itself is contracting. The vast empty voids are shrinking, and galaxies are rushing toward us, not away from us. Their light isn't redshifted, but blue-shifted, as the fabric of space-time itself compresses. The magnificent, complex tapestry of the cosmos is being unwoven, thread by thread, until all that's left is a uniform cloth. The universe is on a relentless march from chaos back to a state of perfect, unimaginable order. The physics of a broken arrow. This journey into a time-reversed cosmos feels like a fantasy. And yet, the question of whether time could run backward isn't just poetry. It's a question rooted in the very laws of our physics. At the most fundamental level, almost all the laws of physics that govern particles are time-symmetric. This means the equations describing their interactions work just as well if time is positive or negative. A movie of two billiard balls colliding looks physically plausible whether you run it forward or backward. For a long time, we thought the universe, microscopically, had no preferred direction of time. But we know from our everyday experience and that relentless increase of entropy that the universe does have a preferred direction. So why does a universe governed by time-symmetric laws have such a strong, irreversible, one-way street character? The plot thickened in the mid-20th century. Physicists discovered that while most interactions are time-symmetric, the weak nuclear force which governs certain types of radioactive decay is not. Experiments showed that the weak force violates a related symmetry called carbon monophosphide symmetry, charge parity. According to a core principle called the Kapton theorem, the universe must be symmetric under the combined operations of charge, swapping matter for antimatter, parity, flipping it in a mirror, and time, running it backward. The implication is profound. If the weak force violates carbon monophosphide symmetry and the universe must obey CPT symmetry, then the weak force must also violate time symmetry to keep the whole thing in balance. In other words, the laws of physics themselves have a subtle, built-in arrow of time. The universe, at its deepest level, can tell the difference between forward and backward. So, could our reversed universe exist? The CPT theorem suggests it's possible, but with a catch. A universe where time runs backward would also have to be one where left and right are flipped and all matter is replaced by antimatter. It would be a true anti-universe. Some physicists have even theorized that the Big Bang might have created two universes. Our matter-filled one moving forward in time, and a mirror antimatter universe moving backward. But simply flipping the arrow of time in our universe runs into the brick wall of entropy and the proven violation of T-symmetry. The initial conditions of our universe, a state of incredibly low entropy at the Big Bang, set the stage for a one-way trip. To reverse it, you'd need to perfectly reverse the momentum of every single particle in the cosmos at the same time, an act so improbable it's effectively impossible. The universe I witnessed, therefore, is not a physical possibility within our known framework. It is a thought experiment that pushes against the boundaries of what we know, and it asks a profound question. Is the arrow of time fundamental, or is it just an emergent feature of our specific cosmic conditions? The future of memory. We return from that place of unburning stars, back to our reality, where time flows in its familiar, forward direction. But the experience leaves an echo. What would it truly mean to exist in a universe where the arrow of time is flipped? The most profound implication isn't for stars, but for consciousness. Our entire experience is built on cause and effect. We act, and then we see the result. We remember the past, but we don't know the future. This is what allows for memory, learning, and the very story of our lives. In a time-reversed universe, you wouldn't remember the past. You would remember the future. Your memories would be of events that haven't happened yet from your point of view. You'd be born with full knowledge of your death, and each passing moment would be a step toward forgetting your birth. Cause and effect would be flipped. The pain would come before the injury. The window would shatter, and then the ball would be thrown. What would life be like? Would there be free will? If you remember falling down the stairs tomorrow, could you choose to avoid them? Or is the act of remembering the future the very thing that causes it to happen? It's a dizzying, paradoxical loop. Perhaps the most startling idea is that our beginning could be another universe's end. The Big Bang, our ultimate origin of low entropy and high order, looks suspiciously like the endpoint of a contracting, time-reversed universe collapsing into a big crunch. Could they be one and the same? Could our universe be the forward half of a cosmic cycle, born from the death of its antimatter twin? We stand on the shore of a vast cosmic ocean, able to see only the waves that have already reached us. Our journey has been to imagine standing on the opposite shore, watching those same waves retreat from the beach and head back out to sea. It forces us to see our own existence in a new light. The decay we see all around us isn't necessarily a descent into oblivion. It might just be one direction in a much grander story. Perhaps, in another corner of the cosmos, the light from a dying star is being called home, its story unwritten, not to be forgotten, but to be made new again. What do you think? Could a universe with a reversed arrow of time really exist, maybe as a mirror to our own? And what would it be like to remember the future instead of the past? Let us know your thoughts in the comments below. Physicists found a place where the future is a memory, close your eyes for a moment. Picture a glass falling from a table. It hits the floor and shatters into 1,000 glittering pieces. Now, imagine watching that scene in reverse. The shards slide across the floor, gathering together, reassembling with impossible precision until the glass leaps back onto the table, perfectly whole. You can imagine it because you've seen a video rewound. But what if this wasn't a trick of technology? What if, somewhere in the vastness of the cosmos, this is simply how reality works? A place where the future isn't something you wonder about, but something you remember. A universe where time's river flows not towards the unknown, but back towards its source. This isn't just a fantasy. It's a possibility that physicists are wrestling with right now. And the ideas they're uncovering might just change how you see everything. Tonight, we're going to drift off on a journey into one of the most profound and unsettling ideas in all of physics. We'll be exploring a hypothetical, yet plausible, corner of existence where time flows backward. A place where smoke unspools from the air and flows back into a cigarette, where the ripples on a pond converge to a single point just before a stone leaps out. This is a journey into the strange physics of a universe where the future is a memory and the past is an undiscovered country. Think of this as a story designed to spark your imagination, to give your mind a vast and wondrous landscape to wander through as you drift towards sleep. We'll gently unravel the deepest mysteries of time itself, exploring the concept of reversed entropy, the cosmic arrows that dictate the flow of events, and whether our perception of a one-way street for time is just a local cosmic bylaw, not a universal decree. We experience time as an unyielding march forward. You are older now than when this sentence began. You remember the beginning, but you can only anticipate the end. This intuitive feeling is what physicists call the arrow of time, and it's almost entirely governed by a concept known as entropy. Think of entropy as a measure of disorder. A neatly stacked deck of cards is a low-entropy state. It's orderly and specific. A shuffled deck, scattered across a table, is a high-entropy state. It's disordered and chaotic. The second law of thermodynamics, one of the most fundamental rules of our universe, states that the total entropy of a closed system can never decrease over time. Everything tends to move from order to disorder. That's why you can scramble an egg, but you can't unscramble it. The universe itself began in an incredibly special, highly ordered, low-entropy state, and it has been getting messier ever since. But here's the central puzzle. Most of the fundamental laws of physics don't actually care about the direction of time. Whether you run the equations for gravity or electromagnetism forward or backward, they work just as well. A movie of two billiard balls colliding looks just as physically plausible if you play it in reverse. This is called time reversal symmetry, or T-symmetry. So, if the underlying rules are reversible, why is our reality so stubbornly irreversible? Why do we only ever experience time flowing in one direction? Stick with me as we venture into the quiet depths of the cosmos to find the places where this rule might be broken, and where the future is nothing more than a recollection. The one-way street we call time. Let's begin our journey on familiar ground, with the arrow of time we all know and live by. It's as intuitive as breathing. The past is fixed, a landscape of memories we can visit but never change. The future is a fog, a realm of possibilities that solidify into the present moment by moment, only to immediately recede into the past behind us. This one-way flow is what physicists call the thermodynamic arrow of time, and it points in the direction of increasing entropy. Imagine the universe at its very beginning, just after the Big Bang. It was a searingly hot, incredibly dense soup of particles. You might think this sounds chaotic, like a high-entropy state. But in the context of the entire universe, it was the opposite. The matter and energy were spread out with almost perfect uniformity. Now, this is where our intuition can be misleading. In a universe governed by gravity, a smooth, even distribution is actually a state of profound and improbable order, a state of extraordinarily low entropy. Gravity wants to pull things together. It wants to form clumps, stars, galaxies, and eventually, black holes. A perfectly smooth gas filling all of space is like a pencil balanced perfectly on its tip. It's an incredibly special arrangement that is destined to fall into a more disordered, clumped state. That uniform, hot, dense state of the early universe was the cosmic equivalent of that perfectly balanced pencil. And for the last 13.8 billion years, it has been falling, clumping together under gravity, forming complex structures, and in doing so, relentlessly increasing the universe's total disorder. This relentless increase in entropy is what gives time its direction. It's the reason coffee cools, buildings crumble, and we grow older. This seems straightforward enough. But when we look closer at the fundamental equations that describe the behavior of particles and forces, a deep paradox emerges. Most of these laws are time-symmetric. This means that the rules that govern reality at its most basic level have no preference for a past or a future. The laws of Newtonian mechanics, which describe the motion of planets and projectiles, are perfectly reversible. Run the clock backward, and the equations still hold. The same is true for Maxwell's equations of electromagnetism and for the strong nuclear force, the powerful glue that holds atomic nuclei together. Let's return to that classic example. A break shot in a game of pool. You see the cue ball strike the tightly packed triangle of balls, sending them scattering across the table. Disorder increases. Now, imagine you filmed this and played it in reverse. You'd see the scattered balls rolling across the table, converging from all directions, and reforming into a perfect triangle, kicking the cue ball back toward the cue. You would immediately know this was a video playing backward because it feels impossible. But from the perspective of the physics governing the collisions of the individual balls, the reversed version is perfectly valid. The reason we never see this happen is a matter of probability. There are astronomically more ways for the balls to be scattered across the table, a high entropy state, than there are ways for them to be in a perfect triangle, a low entropy state. So, while the laws of motion allow for the reversal, the laws of statistics make it a virtual impossibility on a large scale. This is the time reversibility paradox. The microscopic laws of physics are like a road that allows for two-way traffic, yet the macroscopic world we live in behaves like a one-way street. For decades, this was a profound puzzle. It seemed that time's arrow wasn't forged in the fundamental laws themselves, but emerged purely from the statistical tendency toward messiness, driven by the universe's uniquely ordered starting point. But as physicists peered deeper into the subatomic world, they found a crack in this perfect mirror of time. A tiny, almost imperceptible flaw that proves the universe does, in fact, have a subtle, built-in preference for one direction of time over the other. The cracks in time's mirror. For a long time, the perfect time reversal symmetry of the fundamental laws seemed absolute. But there is one force that plays by slightly different rules: the weak nuclear force. This is the force responsible for certain types of radioactive decay, and it's a crucial force that helps power the sun. But it's also the source of a profound wrinkle in the fabric of spacetime. To understand this wrinkle, we need to talk about a trio of fundamental symmetries in particle physics: charge, C; parity, P; and time, T. Charge conjugation, C, is the act of swapping a particle with its oppositely charged antiparticle. Parity, P, is like reflecting the universe in a mirror. And time reversal, T, is, as we've discussed, running the clock backward. For years, physicists believed the universe was symmetric under each of these transformations individually. But in 1957, it was shockingly discovered that the weak force violates parity, P, symmetry. The mirror image version of some particle decays simply does not happen in the same way. It was soon found that the weak force also violates charge, C, symmetry. Physicists noticed something remarkable, though. Even though the weak force violated C and P individually, it seemed to respect the combined symmetry of CP. If you swapped all the particles for their antiparticles and reflected the event in a mirror, the resulting process looked identical. It was thought that this combined CP symmetry was a perfect, unbroken law. That belief was shattered in 1964. Experiments with particles called neutral kaons showed that even the combined CP symmetry was violated by the weak force, though only by a tiny amount. This discovery was so important it earned its own Nobel Prize. It meant that the laws of physics are not the same for matter and antimatter, even when viewed in a mirror. And this is where it all connects back to time. There is a deeply embedded theorem in physics called the Kapton theorem. It states that any sensible physical theory must be symmetric under the combined action of all three transformations: charge, parity, and time. CPT symmetry is considered one of the most bedrock principles of physics. The implication is profound. If the universe violates CP symmetry, but it must preserve Kapton symmetry, then it follows that it must also violate T symmetry to compensate. The violation of CP forces a violation of T. This was a stunning theoretical conclusion. The laws of physics themselves must contain an inherent direction of time. For decades, this T violation was only an inference. But direct experimental confirmation finally came in 2012 from the Babar experiment at the SLAC National Accelerator Laboratory. Physicists there studied particles called B mesons, which can transform into their antiparticles and back. They measured the rate of a B meson transforming from one state to another and compared it to the rate of the time-reversed process. They found that the rates were not the same. The forward and backward transformations did not happen with equal probability. This was the first direct, unambiguous observation of time reversal violation. The universe, at the level of the weak force, can indeed tell the difference between forwards and backwards in time. It's important to put this into perspective, though. This violation is incredibly subtle and only appears in the rare interactions governed by the weak force. It does not explain the overwhelming, macroscopic arrow of time that makes eggs scramble and coffee cool. That arrow is still primarily a consequence of the universe's special beginning. What T-symmetry violation shows us is something deeper. It tells us that time's arrow isn't just a statistical phenomenon. There is a tiny, fundamental arrow embedded in the laws of physics themselves. It's a clue that the symmetry between past and future is not perfect. And as we'll now see, when we journey into the even stranger world of quantum mechanics, those cracks begin to widen. Whispers of reversal in the quantum realm. Now we shrink down, far smaller than an atom, into the bizarre world of quantum mechanics. Here, the solid rules of our everyday experience dissolve into a fog of probabilities. And it's here that physicists are finding that the arrow of time is not just cracked, but can be bent, broken, and may even point in two directions at once. Let's start with an experiment that seems to defy a basic rule we all know. Heat always flows from a hot object to a cold one. But recent experiments have shown that in the quantum world, this isn't always true. In one such study, an international team of scientists used the nuclei of atoms in a molecule and used magnetic fields to make one nucleus hotter and the other colder. Normally, heat would flow from hot to cold. But the physicists first established a special link between the particles called quantum correlation. This correlation contains information, which acts like a kind of fuel. When the correlated particles were observed, the scientists witnessed the impossible. Heat flowed spontaneously from the cold nucleus to the hot one. The cold particle got colder, and the hot particle got hotter. For this tiny, two-particle system, the local arrow of time was reversed. The entropy of the two particles actually decreased. Now, this doesn't violate the second law for the entire lab. The process of creating the correlations in the first place generated more entropy elsewhere. But it demonstrated something incredible. The arrow of time isn't absolute. It can be relative, with different systems having arrows that point in different directions. This leads to an even more mind-bending idea: the superposition of time itself. In quantum mechanics, a particle can exist in a superposition of multiple states at once. Theorists and experimentalists have applied this principle to time's evolution. A team of physicists proposed and then observed a quantum system that was, in a sense, in a superposition of evolving both forward and backward in time simultaneously. They devised a process that could reverse the natural spreading of a quantum system, like reversing ripples in a pond. For a system of 2 quantum bits, qubits, they achieved this reversal with an 85% success rate in one experiment. Adding a third qubit made it harder, succeeding only 50% of the time, showing how quickly the forward arrow asserts itself as systems get more complex. Building on this, researchers have shown through mathematical analysis that even in open quantum systems, which interact with their environment, the underlying equations can remain perfectly time-symmetric. Instead of one dominant arrow of time appearing, their model predicted the emergence of 2 opposing arrows. The system could evolve towards its most disordered state both in the forward direction of time and in the backward direction. This doesn't mean time travel is possible. It suggests that the direction of time may not be a fundamental property, but an emergent feature that might depend on your perspective. If exploring these strange corners of physics sparks your curiosity, consider subscribing. We look into mysteries like this in every video, turning the universe's biggest questions into journeys for the mind. Your support helps us continue to unravel the cosmos. Now, let's venture even further out, beyond the quantum and back into the cosmos itself, to seek out a place where this reversed time might actually exist on a grand scale. A universe in the rearview mirror. We've seen how the arrow of time can bend in the quantum realm, but could an entire region of the universe have a reversed arrow of time? To explore this, we have to confront the biggest mystery of all: why our universe began in such a state of improbable order. As we discussed, the very early universe was incredibly smooth, a state of profoundly low entropy for a system governed by gravity. This is the ultimate source of our arrow of time. But why did it start this way? The laws of physics don't require it. This special starting condition is simply put in by hand to make our theories work. It's a deep puzzle in cosmology called the past hypothesis. Physicist Sean Carroll has proposed a breathtaking possibility. It relies on the idea that our universe might be part of a much larger multiverse. Let's think about entropy again. The highest possible entropy state for a universe like ours isn't a chaotic soup of particles. It's cold, dark, empty space. Over immense timescales, all stars will burn out, all black holes will evaporate, and the universe will settle into maximum disorder, the heat death of the universe. But forever is a very long time. In the quantum world, fluctuations are always happening. Over truly astronomical timescales, it's statistically likely that a random quantum fluctuation will be large enough to birth something new. Most will be small. But given an infinite amount of time in an eternal, high-entropy multiverse, eventually, a fluctuation will occur that is so extreme it spontaneously creates a new, low-entropy state, a configuration that looks just like the Big Bang. This is the core of the idea. Our Big Bang wasn't the absolute beginning. It was just a random, statistical fluctuation out of a timeless, high-entropy parent universe. Now, here is the crucial part. Once such a low-entropy state appears, it will naturally evolve in the direction of increasing entropy. For any beings that arise within that bubble universe, their arrow of time will point away from that initial moment. They will remember the Big Bang as their past. But this process is symmetric. The laws of physics don't distinguish between forward and backward time. Therefore, a single low-entropy fluctuation, our Big Bang, would create 2 arrows of time, pointing in opposite directions. Imagine it as a central point of extreme order. From this point, one universe ours expands outward, with entropy increasing and time flowing forward. Simultaneously, another universe expands in the opposite temporal direction, also experiencing an increase in its own entropy. Beings in that universe would see their cosmos expanding and becoming more disordered. They would remember their Big Bang as being in their past, just as we do. But their future is our past. And our future is their past. They would look out at their night sky and see a universe where galaxies are rushing together, where stars are absorbing light, and where everything is moving toward a state that we would call the beginning. For them, the future is a memory of a hot, dense state. In this magnificent vision, our entire universe is just one side of a temporal coin, born from a random event in an eternal, chaotic sea. There could be another universe, a mirror image, where time flows backward relative to our own. We could never reach it, because to do so would mean traveling back to the Big Bang, the Janus point, from which both futures spring. But its existence would solve the great mystery of our own arrow of time. Our past wasn't special by design, it was special by chance. And for every universe like ours with a forward-pointing arrow, there might be a twin with an arrow that points back. The multiverse of mirrored timelines. This idea of a twin universe with a reversed arrow of time is just one flavor of an even broader, and yes, even more speculative concept: the multiverse. The idea that our universe isn't unique opens up a dizzying array of possibilities for how time might behave elsewhere. Let's revisit the Captain theorem, that unbreakable symmetry of charge, parity, and time. The theorem implies that a universe made of antimatter, C, which is a mirror image of ours, P, and where time runs backward, T, would evolve according to the exact same physical laws as our own. This opens the door to the possibility that the Big Bang didn't just create our matter-dominated, forward-in-time universe. It might have simultaneously created a CPT reversed twin. This mirror universe would be made almost entirely of antimatter. Left-handed particles here would be right-handed there. And most profoundly, its clock would tick in the opposite direction to ours. An observer in that universe would perceive their time as moving forward, just as we do. They would see our universe as the one where time is running backward. Who's to say which direction is correct? The physics suggests both are equally valid. This idea connects elegantly to the work of physicist Richard Feynman, who proposed that an antiparticle could be viewed simply as a regular particle traveling backward in time. Other models also point to this temporal duality. One, developed by Julian Barber and his colleagues, used a computer simulation of particles interacting only under gravity. They found that the system would always evolve from a state of minimum size and maximum density, a Janus point, named after the two-faced Roman god. From this point, the system would then expand outward in two opposite temporal directions, creating two distinct arrows of time. Another model, from physicists like Alan Guth and Sean Carroll, suggests that within the framework of eternal inflation, our universe and its backward-in-time twin may have been born out of a parent universe. We live in one of the branches, experiencing what we call forward time, completely unaware of the other branch where everything is happening in reverse. These multiverse theories are, of course, on the very frontiers of theoretical physics. But they are not mere fantasy. They are plausible scenarios that arise from our best attempts to understand the origin of the universe and the fundamental nature of time. They suggest the single, forward-marching timeline we experience may be just a local perspective in an infinitely more complex and symmetric cosmic structure. Somewhere, in a reality parallel to our own, the future has already happened. It is written not in a book of destiny, but in a book of memory. We began our journey tonight with a simple, familiar observation. Time flows forward. A glass shatters, but never reassembles. We remember the past, but not the future. We took this seemingly obvious fact and held it up to the light of modern physics, only to watch it fracture into a kaleidoscope of strange and beautiful possibilities. We saw that on the most fundamental level, most of the laws of nature are indifferent to time's direction. We found the first subtle flaw in this symmetry in the strange behavior of the weak nuclear force, which proved that the universe does have a tiny, built-in preference for a temporal direction. Then, we descended into the quantum realm, a place where the arrow of time loses its authority. We witnessed experiments where heat flowed from cold to hot, locally reversing entropy. We discovered systems that could exist in a superposition of evolving both forward and backward in time. Finally, we scaled back up to the cosmos itself and confronted the mystery of our low entropy beginning. This led us to the breathtaking idea of a multiverse, where our Big Bang was but a random fluctuation in a timeless sea. A fluctuation that could have given birth to two universes. One, ours, where time moves forward, and a mirror twin, where time flows backward, and the future is something to be remembered. So, what does this all mean? It means that the unyielding, one-way river of time that shapes our lives is likely not a fundamental, ironclad law of reality. It is an emergent property, born from the statistically improbable, highly ordered state of our universe's birth. Our arrow of time is a local phenomenon, a feature of our specific cosmic neighborhood. Physics not only allows for places where time might run backward, it almost seems to hint that such places should exist, whether in the strange dance of quantum particles or in entire universes beyond our own. There are no time machines here, no way to revisit our own past. But there is a profound shift in perspective. The flow of time is not a master we are subservient to. It is a current we happen to be in. As you drift off to sleep, let your mind wander to that other current. Imagine another you, in another universe, looking back on their day. For them, the sun is rising in the west. The coffee in their cup is slowly unmixing, cream and black separating into perfect layers. They are not wondering what tomorrow will bring. They are simply remembering it. And perhaps, in their quietest moments, they wonder if a twin of them exists, somewhere, moving in the other direction. Sleep well. Your past is an illusion, the future is a dream. What if I told you that every moment of your life, your first step, your graduation, the day you fell in love, even your final breath all exist right now, written into the very fabric of space-time? What if the past isn't some ghost, and the future isn't just a dream, but both are as real and solid as the ground beneath your feet? Modern physics suggests your past isn't gone, and your future has, in a way, already happened. It's a concept so staggering it feels like it could break your mind, because it challenges the very core of how we experience life. We feel time flow. We remember yesterday and we plan for tomorrow. How could it possibly be any other way? We're about to journey to the very edge of what we understand about reality. We'll explore the science that says the past, present, and future are all equally real, and that the steady march of time might just be a profound, stubbornly persistent illusion. We'll start with the mind that first shattered our intuitive grasp on time, Albert Einstein, and follow his logic to its startling conclusion. A universe where nothing truly happens, but simply is. And once we've built this strange new model of the cosmos, we'll ask what it all means. For our lives, our choices, our sorrows, and the quiet mystery of just being here. Because if your life is a story that's already been written, what does that make you? The author, the reader, or the character living it all out, moment by glorious, terrifying, beautiful moment? The Einstein entry point. Shattering the universal clock. Before the 20th century, our picture of time was simple and, honestly, made a lot of sense. It was the universe according to Sir Isaac Newton. In his world, time was like a grand, cosmic clock. It ticked at the same rate for everyone and everything, no matter where you were. A second on Earth was a second on Mars, was a second in a galaxy a billion light years away. Time was this steady, invisible river carrying all of reality along in its current. It felt right. My now feels like your now. It feels like we all share one single, universal present moment. And then, in 1905, a 26-year-old patent clerk in Bern, Switzerland, took a hammer to that idea. His name was Albert Einstein, and his theory of special relativity would change our relationship with time forever. Einstein's revolution started with a simple observation. The speed of light in a vacuum is constant for everyone, no matter how they're moving. That might not sound world-shattering at first, but trust me, the implications are enormous. Imagine you're in a car going 50 miles per hour and you switch on the headlights. You'd think the light from your car is moving at the speed of light plus 50 miles per hour, right? But it's not. It's just the speed of light. Now, if another car is driving towards you, the driver in that car will also measure your headlight beam traveling at the exact same speed. It doesn't matter how fast you're going or in what direction. The speed of light is the universe's one unbreakable speed limit. For that strange fact to be true, something else we thought was absolute has to be flexible. That something is time itself. Einstein realized that if the speed of light is constant, then time must slow down or speed up to make the math work. This is the famous phenomenon of time dilation. The faster you move through space, the slower you move through time. And this isn't a metaphor or a trick of perception. It's real. Astronauts on the International Space Station, zipping around the Earth at 17,000 miles per hour, are aging just a tiny fraction slower than we are. Their clocks and their own bodies are literally ticking at a different rate. If you took a trip on a spaceship at 99% the speed of light for what felt like 1 year to you, you'd come back to an Earth where decades had passed. You would have traveled into the future. This one insight demolishes the idea of a universal clock. If our clocks tick at different rates depending on our motion, then our experience of time is personal. And if my measurement of time is different from yours, then my definition of now must be different, too. This leads to something even stranger: the relativity of simultaneity. In plain English, it means that events happening at the same time for me might not be happening at the same time for you. Imagine you're standing in the dead center of a moving train car. Just as you pass a friend standing on a platform, lightning strikes the very front and the very back of the train. From your perspective in the middle, the light from both strikes reaches your eyes at the same instant. You'd correctly say the strikes were simultaneous. But what does your friend on the platform see? From their point of view, the train is moving. So the light from the rear lightning strike has to travel further to reach them than the light from the front strike. To your friend, the lightning hit the front of the train before it hit the back. So who's right? You, who saw it happen at the same time. Or your friend, who saw two separate events. Relativity says you both are. There is no single, objective, now. My now is just my slice of space-time. Your now is your slice. And if we're moving relative to each other, our slices are angled differently. What I call the present can contain events that are in your past or even your future. This isn't just a thought experiment. It's how your phone works. The GPS system relies on satellites moving at high speeds in a weaker gravitational field. Both of these factors warp time, causing the satellite clocks to tick about 38 microseconds faster per day than clocks on the ground. If engineers didn't constantly correct for these relativistic effects, your GPS would be off by several miles within a single day. So, time isn't a universal river. It's more like a personal stream whose flow depends on your speed and surroundings. That alone is a radical idea. But it's just the first step. The truly mind-bending part comes when you apply this idea to the entire universe. If there is no universal now, and my present can be your past. What does that say about the past and the future? It implies they must be just as real as the present. Because if someone else's now can contain what you consider the future, then that future must already exist. This is the gateway to the block universe. The block universe and the arrow of time. If we accept what Einstein's relativity tells us, we're forced into a very weird picture of the universe. The common sense idea that only the present moment is real, which philosophers call presentism, becomes almost impossible to defend. If your present and my present are different, which one is the asterisk real one? The logical answer is that all moments are equally real. This is the core idea of a theory called eternalism, or, more poetically, the block universe. Picture the universe not as a movie that's playing, but as the entire film reel itself. Every single frame from the Big Bang to the final flicker of the last star exists all at once. Or, think of it like a giant loaf of bread. Each slice is a snapshot of the entire universe at one moment. Your birth is a slice near the beginning. This moment, right now, is another slice. Your death is a slice further down the loaf. From this perspective, all the slices exist together as one complete, four-dimensional block of space-time. The past isn't gone. The future isn't unwritten. They're just other locations in space-time, the same way Paris is another location in space relative to Tokyo. They're all just there. In this model, the feeling we have of moving through time is an illusion. Nothing is becoming, everything simply is. The physicist Hermann Weyl famously said, "The objective world simply is, it does not happen." Your consciousness is like a spotlight moving along that loaf of bread, illuminating one slice at a time, creating the powerful impression of a flowing present. But the slices your spotlight has passed over still exist, and the slices it hasn't reached yet are already there, waiting. Your entire life is a permanent fixture in this block. This is the conclusion that led Einstein to write to the family of his lifelong friend, Michel Besso, after his death. "Now he has departed from this strange world a little ahead of me," Einstein wrote. "That means nothing. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." For Einstein, his friend wasn't gone. He was just in a part of space-time that Einstein could no longer get to from his own now. But this raises a huge, obvious question. If the block is real and all of time exists at once, why do we only experience it in one direction? Why do we remember the past, but not the future? Why do eggs break but never spontaneously unbreak? The fundamental laws of physics, like gravity or electromagnetism, don't care about the direction of time. A video of planets orbiting a star looks just as valid forwards as it does backwards. Yet in our world, time clearly has a one-way street sign. There is an undeniable arrow of time. The answer, it seems, comes from a different corner of physics. The second law of thermodynamics. And the key word is entropy. Entropy is basically a measure of disorder or randomness. The second law says that in an isolated system like our universe, total entropy, or disorder, will always increase. Things naturally go from order to disorder. An intact egg is a highly ordered, low-entropy system. When you drop it, it shatters into a disordered, high-entropy puddle. Why? Because there are countless ways for an egg to be a shattered mess, but only one way for it to be a perfect egg. The odds are just overwhelmingly stacked in favor of messiness. Physicists believe this is the origin of time's arrow. Our universe began in a very special state, incredibly hot, dense, and with extremely low entropy. The Big Bang was the most perfectly ordered moment in cosmic history. For the last 13.8 billion years, the universe has been expanding, cooling, and getting messier. Stars burn out, energy spreads out, and things fall apart. The universe is on a one-way trip towards maximum disorder, a state known as heat death. Our perception of time's flow is tied to this relentless march towards chaos. We experience time moving forward because that's the direction entropy increases. The past is the direction of low entropy. The future is the direction of high entropy. We remember the past because memories themselves are ordered, low entropy structures like a footprint in the sand or a specific pattern of neurons in your brain. These records are formed as the universe around them gets more disordered. This process only works one way. You can't have an effect, a memory, before its cause, and causes always precede effects in the direction of increasing entropy. You can't remember the future because the ordered records of it haven't been created yet. So now we have this strange, beautiful picture. Einstein's static, four-dimensional block where all of time exists at once. And layered on top of it, the thermodynamic arrow of time, which gives that static block a direction for us, the conscious beings living inside it. We feel time flowing because our bodies and brains are thermodynamic processes, surfing the great cosmic wave of disorder from past to future. But in solving one mystery, this opens up a Pandora's box of philosophical questions that hit right at the heart of what it means to be human. The philosophical implications. The quiet mystery of being. If we live in a block universe, where our life is already laid out from start to finish, what happens to free will? If my future actions already exist in a future slice of space-time, in what sense do I choose to do them? The feeling of choice is one of the most powerful parts of being alive. I feel like I'm deciding to lift my hand or to speak these words. But if the block universe is real, that feeling might be the grandest illusion of them all. This leads to an idea called determinism. The notion that every event is sealed by the events that came before it. In the block universe, the future isn't just predictable, it's already there, as fixed as the past. When you're at a crossroads, agonizing over which way to go, this model suggests the path you will take is already a settled fact of the universe. The anxiety, the deliberation, that's all real, it's part of your now. But the outcome is already waiting in a future slice. This can feel, well, depressing. If my choices don't really matter, what's the point? If my struggles and triumphs are just pre-written scenes, what value do they have? It can feel like it strips life of its meaning, turning us into actors reading from a script we can't even see. But there's another way to look at it. Some philosophers, called compatibilists, argue that free will and determinism aren't mutually exclusive. They suggest we redefine free will. Maybe it isn't the ability to have chosen differently, but the freedom to act on your own desires without being forced by someone or something else. Even if your choice was determined, it was still your choice, flowing from your unique character and memories. The future is fixed because of who you are, not in spite of it. Then there's the wild card, quantum mechanics. While relativity points to a deterministic block, the quantum world is built on probability and fuzziness. A particle can exist in multiple states at once until it's measured. This inherent randomness at the heart of reality seems to clash with the clockwork nature of a predetermined universe. Some physicists think this quantum uncertainty could mean the future is genuinely open, creating a growing block, where the past is fixed but the future is a branching tree of possibilities. The tension between Einstein's block and the quantum world is one of the biggest unresolved puzzles in physics. Beyond free will, the block universe changes how we think about consciousness itself. Why does now feel so special? In the block model, it has no special status. So why does it feel like the peak of reality? Maybe our brain creates the now. It stitches together senses, memory, and prediction into a seamless present moment that is, in reality, a fraction of a second behind the outside world. The flow of time could be a feature of our consciousness, not a feature of the universe. This perspective can also radically change our relationship with the past. What is grief if the past isn't truly gone? The pain of losing someone comes from their absolute absence. But in the block universe, they aren't erased. They're still there, in the past slices of space-time. The moments of joy you shared aren't just memories. They're permanent fixtures of reality. The loss is not one of annihilation, but of access. You can't reach that part of the block anymore, but it's still there. This doesn't take away the pain, but it might change its character. And it changes how we see the future. Anxiety is often rooted in uncertainty. But if the future already exists, then in a sense, the struggles you're yet to face have already been overcome. The successes you hope for are already achieved. This doesn't mean you should just sit back and do nothing. The you in the future exists only because the you right now does the things that lead there. But it can offer a strange kind of peace, a trust in the unfolding of a story that is already whole. The idea that your past is not gone and your future is already written is one of the most challenging thoughts you can entertain. It feels wrong. It goes against everything we feel in every waking moment. And yet, it's a logical conclusion drawn from our best understanding of space-time. It forces us to confront the possibility that our most fundamental perception, the flow of time, is an illusion generated by our own minds. We feel time flow because we are creatures of entropy, surfing from an ordered past to a disordered future. So, what do we do with this? Does it lead to despair, a feeling that our choices are meaningless? Or could it lead to a different kind of freedom? Maybe knowing that every moment of your life has a permanent place in the universe gives each of those moments an incredible weight. The joy you feel right now isn't a fleeting chemical reaction. It's a permanent feature of reality. An act of kindness isn't a temporary gesture. It's woven into the eternal fabric of what is. The block universe doesn't have to be a prison. It can be a masterpiece. It suggests that our job isn't to fight against fate, but to live out our part of the story with as much grace, awareness, and love as we can. To fully inhabit the slice of now that our consciousness is illuminating, knowing it's our one and only point of contact with the whole story. The past is an illusion because it isn't truly past. The future is a dream because it's already real. All we ever have is this moment. And this moment is eternal. The mystery of being isn't about solving the puzzle of whether we're free or fated. It's about learning to live in the paradox. To act as if our choices matter, while accepting that the story may already be complete. To look at the stars, knowing you are seeing into the past, and to look at your own hands, knowing they will build a future that, in some sense, is already there. If you find yourself thinking about these deep questions long after this is over, I hope you'll stick around for our next journey. The greatest adventures are the ones into the unknown.